they don't accidentally broadcast things that people don't want to see on the board to like a lecture full of people.
Yes, I see, I see.
That's the system.
But then this should work, and then I can do this, and then perfect.
I mean, this would be like for a hacker conference, it would be very appropriate. Like you get 10 minutes before the competition, and you have to screw the projector as hard as you can.
Okay, let's see. What I will do.
So I think you can also wing it
Because?
Ah.
Well, because our mail is all set up.
Okay.
Up to you.
I can.
Fine.
No,
I'll
no,
just spend like.
no, go ahead.
I'll spend 20
Comment
out
ça.
of my 25 minutes trying to. I know there are new things in Sonoma. You don't need to tell me. Interesting. I've implemented the identity.
Tu le vois pas forcément arriver parce qu'il faut que quelqu'un clique. Mais il faut que ton laptop arrive à afficher des choses sur l'autre écran qui devraient apparaître.
Where is the displays? Oh. Okay, so it knows that it has a display.
Yeah, so it might just be working and that.
It just might be invisibly working.
Yes.
Okay, I think we can set it up during the questions. So.
Yeah.
Yeah, I think you're probably fine. Okay. Okay, just then let me look. Yeah. Very good.
Hey, yes, hello and welcome to CoqPL. We're happy to see you all. Please feel free to also use the seats, which are a little bit more up front, because like poor Armel will be very lonely here, and I don't think we will get to the full 500 people in this room. Can't hear you? Okay, perfect. Yeah, it's too far. So yes, welcome to CoqPL. Just for those who want to know, because that's mostly like one of the most popular sessions, the session on the Coq development team will actually be today the second session and not as traditionally the last session, because Mathieu, who has kindly agreed to give this session, will be on a train already at this time. So just for everybody who wants to join the session, this will already be at 11 at the first session. Okay, and otherwise I will give the stage to our invited speaker, Armel, who will talk about Melocoton.
Thank you very much. So yeah, this is Melocoton. This is joint work with all these cool people. Johannes and Simon are at POPL, if you want to talk to them, as well as Lars and Derek. All right, let's get started. So in this work, we are interested in so-called multi-language programs. And these multi-language programs are maybe a bit more common than you might think. A few examples include NumPy, a Python library for fast number crunching, implemented in Python, but with routine in C and Fortran. Firefox includes code in C++, Rust, and JavaScript. Another example is OpenSSL, which is itself a pure C library, but is very useful, so ends up being included in other programming languages with bindings for Rust, Python, OCaml, Go, and so on. So in particular, I was interested in interoperability between OCaml and C programs. And sure enough, if you look on OPAM, you can see that there are some bindings for OpenSSL in OCaml. And if you look at the code, you can see that these are implemented using a mix of OCaml and C code. And the C code does not include the OpenSSL code. It is just a wrapper code that is used to expose the C library as a normal OCaml library that you can use from standard OCaml code. And the way this works is that this wrapper code is going to use the OCaml foreign function interface, or FFI, which is a set of primitives that you can use to write this kind of code. And wrapper code has actually quite a tough work to do, right? Because now it has to bridge between these two very different languages, OCaml and C, where OCaml is a high-level functional language with purely functional data structures, structured values, and so on, and automated memory management with a garbage collector. And on the other hand, C is lower level, has pointers to manipulate memory, and manual memory management. We also want, typically, the wrapper code to be efficient and not introduce unnecessary overhead. So this is kind of a pick 2 out of 3 situation, and as a result, OCaml FFI code is typically very unsafe, and it has to follow many subtle rules dictated by the FFI. And if you fail to follow these rules while writing the code, then you might segfault your program, corrupt its memory, or just break the type safety and data abstraction properties of OCaml. So the question for us was, well, how can we verify the correctness and, say, functional correctness of this kind of code written in different languages with different memory models? If we look at the existing work for verification of functional correctness of single languages, there is a lot of existing work. This is just a sample of papers from our field in the last few years. And if you go and read them all, you can see that there is a sort of recipe that works very well, which is to equip your programming language with a program logic. Maybe you will use whole logic for a simple imperative language, or maybe you need some more modularity or reasoning about aliasing, and you will use a separation logic. But that works fairly well. Now, if we look at the picture for in the multi-language setting, the picture is a bit more sparse. There is some existing work on semantics, in particular in the CompCert setting, and logical relations with Amal Ahmed's work. But here we are really interested in proving the correctness of specific programs that combine these unsafe languages and with the unsafe FFI, but we'd like to be able to prove that for a specific program, this program actually follows the rules and is safe. So this is what we set out to do. And to my knowledge, Melocoton is the first program logic that can deal with these multiple languages with very different memory models. All right. So let's look at a concrete example of this kind of program mixing OCaml and C. And for the sake of the example, we'll say that we'll assume that we have this C function hash pointer, which takes a pointer to an integer and hashes it, replacing the integer in place. And let's say that this function uses state-of-the-art cryptography, and I don't know, like is very complicated, so we want to reuse it off the shelf and not port it to OCaml or something like that. And we want to use it from an OCaml program that does other stuff. So here, for the example, it's going to be a simple program that creates a reference containing an integer, calls some hashref function, which is supposed to go in the reference and hash the integer inside, and then print the content of the reference. And the idea here is that hashref is going to do the same as hash pointer, but on the OCaml reference, by calling under the hood the hash pointer C function. So these two parts don't really connect yet. So what we need to do is to write some what we call glue code, which is going to be implemented in C here, with this extra camel hashref function. And this is going to be a C function, but a C function that receives as an argument and produces as a result OCaml values of this value type in C here. And then the idea is that camel hashref is going to use these operations of the OCaml FFI written in yellow to first read into the contents of the OCaml reference, turn that into some C stuff that it can pass to hash pointer, and then read the hashed integer and write it to the OCaml reference, and finally return unit. All right. And the idea is that overall this function is going to behave just like an OCaml function. And finally, we need to do a last bit of stitching, which is to indicate to the OCaml compiler that whenever we call hashref in OCaml code, then we actually need to just call the camel hashref C function. And this is what we do with this external definition. And we also need to just give an OCaml type for this function, which the OCaml compiler is just going to trust. All right, so this is the complete example for this talk. And as you might guess, the tricky part is the bottom part. It's the part with the glue code. And why? It's because all of the use of this operation is not statically checked. There are many mistakes that we could make, either by misusing the functions of the FFI on the right. Maybe we do some small overflow and read or write outside the block, or we fail to respect some of the other invariants of the FFI. or maybe we write the wrong type annotation on the left. Either way, if we do any of these mistakes, it's not going to be caught by the compiler. The program is going to run, and it's going to explode at runtime. So what we wish to do is to design a program logic that gives us reasoning rules, pre- and post conditions for all of the operations that appear here, so that overall we can statically check those and prove a specification for the overall code that ensures that we have steered away from all the possible mistakes. Very good. And of course, I'm here talking at CoqPL, so I want to do all of this, but also foundationally in Coq, so that I can slap a big verified in Coq badge on top of this. All right. And I have good news, which is that we have a tool to do all of that. It's called Iris. Iris is an expressive separation logic framework implemented in Coq to build custom program logics. Excellent. And to do that, the Iris provides us with a methodology where there are roughly 3 steps. The first is to define some operational semantics for your custom language in Coq. Then you have to define how to interpret the state of a program as a separation logic assertion in Iris to give modular reasoning principle about your state. And then you go through the operations, the primitive operations of your language, and you prove reasoning rules for each of them against this interpretation. Excellent. So it seems we might actually have a simple solution to our problem, right? There seems to be a clear path ahead. Why don't we just, apply the Iris methodology to this big OCaml plus C plus FFI language that we seem to have going on? And it might work. But then I'll let you think for a second of defining just the inductive type for the syntax and semantics of OCaml plus C plus FFI in Coq at once. And you might start to think like me that this is going to be unpleasant and unsatisfactory, both for engineering and conceptual reasons. And indeed, if we look at most multi-language programs, they look like this. A big part of the program is just business logic, either in, say, OCaml or C, that is normal single language code. It's completely oblivious to the other language on the other side, and it is normal code. And then there a tiny part of the code, which is the glue code, is where all the tricky language interaction actually occurs. So there is a lot more structure here than an arbitrary intermixing of the 2 or 3 languages. And so we believe to build the formal account of that, we also want to have some extra structure. And what we say is that we want to follow this extra design principle, which we call language local reasoning. And the idea, first, from an engineering point of view, is that we already have existing formalization, semantics, and program logics for individual languages, say OCaml and C, maybe perhaps in Iris. So we'd like to just reuse those as much as possible. But it's not just about reuse. From a conceptual perspective, if you're writing code in one language, say you are implementing OpenSSL in C, you just want to focus on doing that. You don't want to care about all the other languages that might eventually get linked into your code. You just want to focus on writing a correct OpenSSL implementation, which is already quite hard. So, and on the other side, if you're in OCaml and you call into this OpenSSL library, you don't care about the fact that some of it is implemented in C. You just care about the fact that it encrypts stuff. And it's really the job of the glue code in the middle to make sure that this reasoning actually works, to make sure that we can link these 2 languages in a way that we can later forget that we are talking with a different language on each side. And so this reasoning as if we are mostly in a single language, we call this language locality. And we believe it's quite important that our framework supports language local reasoning. So in Melocoton, we do use Iris, and we do follow the Iris methodology broadly. but where we build the problem logic on top of semantics defined in Coq, but we adapt it a little bit. First, to account for all the weird stuff that is happening in the glue code, we define operational semantics and the problem logic specifically for the glue code, and all of that is new. But we also want the language local reasoning part, and for that, we take existing formalizations for like mini OCaml and mini C that already existed in the Aris world. We tweak them a little bit, and we embed them into our combined semantics and problem logics. And the idea is that at any point, then, when we are verifying a multi-language program, if we are in a part of the code which is in a single language, then we can simply drop down and use the normal problem logic for this part of the code, and reason as if you were in a single language. All of that is verified in Coq and in Aris. And so this is the general idea of how we combine language interaction and language locality. And of course, there is quite a bit of tension between the two that we'll need to resolve. And so in the rest of the talk, I want to give two key ideas of how we make this work. First, I'll explain how we do this language local reasoning embedding of the existing languages and formalizations. And then I will give a second key idea of how we define language interaction. And then I will give you a brief tour of the structure of the Coq formalization. Very good. So the first key idea is that we take existing languages and problem logics, and that by themselves assume that they just work on their own, and we equip that with a new minimal tweak, which is we equip them with the ability to make external calls to the outside. And at this point, from the point of view of each language, we'll just assume that the outside is always going to answer the call and give us the correct answer. All right, so this is a sort of minimal extension for now. An example of external call that we have seen in the OCaml part of the program is the call to href. Okay? Href is not part of the OCaml program. It's just something that is part of the outside. Now, remember the Aris methodology. To give meaning to this new construction, we need to do two things. First, define its operational semantics, and then define how we reason about it in the problem logic. So we do these with these two steps, and for the first one, we do something maybe slightly unusual, which is to say that this actually does not have a semantics from if we just look at this problem. Okay? But so we sort of defer the problem for later. But then in the problem logic, we still want to be able to reason about this problem in isolation. We want to prove something about this problem, that it is correct, maybe. And we want to reason at this point as if the href call was going to work and do what we expect. So in the problem logic, we're going to assume a specification for the call. More specifically, we're going to assume that it has the following specification. So this is in separation logic, so it's a hot triple with a pre and post condition, and the pre and post condition use a points to, which describes the ownership of the OCaml reference. And so we will assume that a href requires ownership of the reference, saying that it contains an integer, and will return ownership of the reference, having updated the integer inside. We don't really care about specifying the hashing. It's just another integer. And then if we just assume this specification for href, we can just now use the normal OCaml problem logic to verify the rest of the problem. Great. Formally speaking, so what we do is that we take the standard separation logic triples that we have in separation logic to express specifications, and we now in Melocoton update those to have an extra parameter, which we call an interface, which we write psi here, and the interface basically just tells us what specification we assumed for the external calls of the problem being verified, E. For completeness, the type in Coq here of this interface is as follows. It's an arrays predicate, which takes the name of the function for the external call being called, the list of arguments, the post condition that we want after, and it tells us the precondition that we have to satisfy in order to be able to make the call. If that sounds a bit mind-bending, that's all right, it is. The important part here is that this is a very general type, which allows us to put arbitrary arrays predicates here to describe the specification of the call. And this is actually a powerful principle that we are going to use to reason about the glue code. What we are going to do there is that we are going to say, I'm just going to verify this glue code using the normal program logic for C, and I will treat all the calls to FFI operations as external calls. Now, these operations of the FFI, so they are not C functions, and they do not behave as C functions, right? They do not operate on the state of the C program. They operate on the state of the ML program, which is in the outside. But that's fine, because what we can do is that we will assume specifications for these FFI operations that are described in terms of new assertions that are specific for the FFI. So whenever we want to reason about a glue code program, we'll just use the C program logic and assume a specific interface psi FFI, which gives us specifications for all the FFI operations. And these specifications now are written in terms of this new block points to predicate, which I will talk a bit about later, but basically describe the glue code view of the OCaml data. And so, for example, store field, which writes into a block, takes ownership of a block points to and returns ownership of an updated block points to, and we have other specs for all the other primitives. And by assuming this interface, now we can use the normal C program logic to verify the rest of the code and prove that camel href has a specification where it takes, for the reference, a block points to in the precondition and produces an updated block points to. Very good. So let's sum up what we have so far. And so this is the code of our complete example. And actually what I've showed is that by simply reusing this single language program logics with minimal tweaks, we can verify all of the code. Excellent. But of course, we have verified all of the code by assuming in isolation that each part of the code assumes that the outside does the correct stuff. So the proofs and the languages are not connected yet. But what the cool part here is that actually we could still go over all of the code and prove some stuff. So now what's left to do is to actually connect all of the proofs and show that everything fits together. And the key idea is how we do this. The second key idea is how we do this. All right, so to zoom in a little bit, what we have is that we have assumed on the OCaml side that href follows this OCaml specification. And we have proved on the C side that camel href has this other specification. But now in the code, when we call href, this is just going to call camel href. So the two are not really connected at that point yet. They are more or less the same function, but we have two different specifications that have two different logical views about the same piece of state, which is this OCaml reference. So what's going on here? Let's back up a little bit and just look at what's happening in the code. So more broadly, the question here is, how is OCaml data accessed from the C glue code? And the answer is that C glue code can completely access the OCaml heap. So what here, they are really operating over shared memory. The glue code is just going to read into the OCaml heap, but is going to access this OCaml heap using a different memory representation than what is used by the OCaml code. It's going to use this lower level block representation of the ML values in terms of blocks and integers. So a bit more precisely, this is a PL talk, so we have to have a nice notation. Tilde ML And we write tilde ML to say that a high-level representation of an OCaml value is related to a lower-level block representation as used in the glue code. For integers and booleans, these are just represented as integers. True and false become 0 and 1. Now, if we have more structured values, such as arrays and reference on the high-level OCaml side, these are just going to be represented as blocks. And a reference is going to be a block of size 1, an array a block of the same length as the array. And the same holds also for immutable data. So if we have a pair, it's also just going to become a block of size 2. And lists become linked lists in memory of these blocks. So on an example, if in OCaml code we create a reference on some nested pairs, the high-level view of the OCaml program in this normal semantics would be that we just create a location in the heap that holds the structured pair, which is just a structured value. But now, the glue code view of this data is that actually we have allocated 3 blocks, 1 block for the reference, but also 2 blocks for the pairs. And these are really heap allocated in this heap of blocks. So remember the Aris methodology. We need to define some operational semantics for that. And so on one hand, remember that we embed the existing operational semantics for ML. So we'll have a high-level heap that you would get from any standard operational semantics, which you write sigma here, which corresponds to the high-level view of the OCaml heap. But then when defining the operational semantics for the glue code that we need to define, it's much more convenient to reason in terms of a heap of blocks, according to this block-level representation that we have seen. So now we have these 2 heaps that represent the same data. So we need to sort of keep them in sync. And actually, what we are going to do is that we are never going to have the 2 heaps at the same time, but switch between the 2. And we are going to switch between the 2 whenever we are at a language barrier, which means that if we are running ML code according to the standard ML semantics, then we'll use the standard heap of this ML semantics. And then at some point, we'll make an external call. And boom, we are going to take all the high-level heap and translate it into this block-level heap. Then we run in the glue code, which operates on this block heap. And the glue code eventually returns. And at that point, the semantics will just take all this block heap and turn it back into an ML heap. Excellent. So to unfold this a little bit more, if we now consider the whole state of a multi-language program mixing OCaml and C, its entire state, I've omitted some administrative parts, but conceptually its entire state is going to be a pair of an OCaml heap and a C heap for the C data, for the C part of the program. And say we start by running ML code. This is going to update the ML heap, make an external call at some point, and then the glue code semantics kick in and turn our ML heap into a block heap. Then we run some C code, which might update the C heap. The C code might eventually call an FFI operation. Then the glue code semantics implement this operation and modify the block heap. And then this returns eventually and turns all the block heap into an ML heap back. All right. So to define the semantics of the interaction between these 2 languages, the operational semantics, this works. This is what we do. But now we need to define the program logic side of this. And here, it is a bit more tricky to make something that actually works and is nice to use. So for now, let's try something naive and see why it doesn't work. And we'll take it from there. So we are doing some separation logic. So we'll have our points twos. Points two is how we reason locally about the state. So a single points two describes the contents of a single location in a heap. And then we have a bunch of points twos that together describe the contents of the whole heap. And we have these 2 heaps. So we have 2 kind of points twos, 1 for each. But then the idea, the issue, as I've just showed, is that we never have these 2 heaps. We just switch between one and the other. So when we go from ML to C, the ML heap disappears. So what should happen to these ML points twos? One simple idea would be to just do the same. We'll just take all the points-twos and turn them back into block points-twos. And whenever we go back, we do the same. We take all the block points-twos and turn them all into ML points-twos. All right? So this means that the rule for the reasoning rule in separation logic for an external call would look like this. If you want to call into a function from ML, call a C function from ML, as a precondition, you would have to provide all the ML points-twos. You would get back all the block points-twos in return, and the reverse operation at the end. All right. As some of you might have guessed, this is a very bad rule. It's extremely bad. It's very non-local, non-modular. It doesn't really work. Why? Because in separation logic, we also have this rule, which is emblematic of separation logic, called the frame rule. And the frame rule is very good. We like the frame rule. It says that if we can verify a program E with pre and post condition P and Q, then all of the other resources we have not talked about are not modified. So we only need to talk in the pre and post condition about the stuff that we need. That's very nice. So if we have some other stuff R, we can just put R in pre and post, and it's completely preserved. Excellent. But now if we specify the frame rule with the call a C function operation, and then R with a random ML points-2, these rules mean that we can just forget about ML points-2 that we do not use. And now this is incompatible with the other rule that tells us that you have to give all the ML points-2s in the world in order to make a call. So these rules are incompatible. And at a high level, what's happening here is that on one hand, the semantics are defined by operating globally in the state, which is fine for operator semantics. But in the program logic, we want nicer local reasoning rules. So we cannot just do the same in the two layers. So the approach that works, the better approach, is to somehow make it so that OCaml points-twos remain valid when switching to the C code. So that means that we will have this cloud of ML points-twos, and then we call to some C code, and they are still there. All right. But maybe now the glue code is interested in accessing some of these points-twos, maybe some location L1 in the ML heap, but it cannot directly operate on it. It operates on its block level representation. So what we'd like to do is to turn this ML points-2 into a block points-2. Maybe we need another one. So we just turn another one into a block representation, operate on them, and then when we're done, we'll turn them back into ML points-2s, back into the code of ML points-2s. All right. And this means that overall, we have proved for a C function that it has a specification that can be expressed in terms of just ML resources, which is very nice because it means that now it should be safe to use from ML code, which is exactly what we wanted. So formally speaking, we justify this reasoning by providing these two view reconciliation rules that allows us to convert on demand between these two views of memory. The first rule tells us that you can take an ML points-2 and turn it into a corresponding block points-2 with related contents according to tilde ML, if you remember tilde ML, and related addresses. And the other rule tells us that you can go in the other direction, take a block points-2 with some contents that are related to some high-level contents and turn it into a ML points-2. So these are very nice rules because you can just use them whenever it's convenient in your proof. So how do we justify that these rules are correct? Good question. So the issue, again, is that whenever you're running ML code and you make an external code, the ML heap disappears. So what do we do here? What we do is that we'll have some extra ghost state, right, as you do in arrays. And we just have some extra ghost heap of the ML, an extra ghost ML heap that backs all the ML points-2 so that they are still tracked by the system. But then this ghost heap cannot be completely arbitrary. It sort of still needs to stay in sync with the block heap that is now here in the operational semantics. And defining this correspondence is subtle and really the crux of capturing the right reasoning principles for the FFI, because it needs to be not too tight, so as to allow weird low-level hackery that the FFI needs to do sometimes, but also not to lose, so that we still have the view reconciliation rules. And I'll spare you the details. All right, so that's the idea. But now the good news is that we can finish the proof for href. So on the ML side, we assume this. Now we can use the proper rule for external calls, which is much nicer now and looks like this. It says that if you're in ML at the bottom, and you want to reason about an external call to a C function f, passing it an ML value x as an argument with pre and post condition p and q, then you can just reason about the call in C about the function f with a different C value as an argument, necessarily. But now this C value v, you can just assume that it is related in terms of tilde ML to the ML argument x. And the precondition is the same. You just get to keep your precondition. And in the post condition, you just have to prove that you can return the C value, which is related to something that satisfies the post condition. So basically, on this example, that means that in the precondition, you can still have your ML points to ownership, and you have to give it back in the post condition. And the argument and return value are related to the C values that you actually receive. In the post condition, you have to return unit, which is related to value unit, all right? But now we want to operate on this reference in terms of these FFI operations, so we need to turn it into a block points to using view reconciliation rule number 1. We do our stuff, and then at the end, we need to turn it back, so we use view reconciliation rule number 2 to go from block points to an ML points to. And having done these 2 steps at the boundary, we are done, because we have shown previously that the rest of the code works as we expect on these block points to. So the proof is done. Very good. And I could stop here, but we're at CoqPL, and I have not shown so far any line of Coq syntax, so this would not do. So let me do now a brief overview, a tour of the structure of the Coq formalization. And the Coq formalization is structured around this notion of language. If you're familiar with the Iris language interface, it's not too different. It just adds stuff for external calls. And so a language defines, so it's parameterized by a type of values, and it defines some operational semantics for the language with a type of expressions, state, and then a stepping relation between pairs of expression and states. All right? But now we have the stuff about external calls, so we want to first define that if we have a program, other people, the outside, can call into this program, and the program is going to be a collection of top-level functions. So we have a type for a top-level function, and a function that tells us if you call a top-level function and pass it a list of values, then you get this computation that you can run. And symmetrically, if you are running a program in this language, this program can make some external calls. So we have something to identify that a given expression is actually currently making an external call with a function name and some arguments in some evaluation context. And that's basically it. And yeah, so lastly, then we say that a program of a given language is just a collection of top-level functions with top-level function names. And you can think about this as a program, sort of a program module, or maybe the language level equivalent of a .o file. It's just a piece of code that you can call into and that can also call some other external piece of code. So yeah, so now the question is, can we do linking about these languages and programs? So can we do the equivalent of LD linking two .o files together and obtaining an executable? But we want to do this then at the language level for these language interfaces. So maybe we will take some two languages which have a common type of value, at least. And then can we have two programs? Maybe a program P1, which implements function F1 calling to an external function F2, and then a program P2 with defining a function F2 that calls an external function F1. These belong to two languages, so there are some ... here, but the code could be different. Then what we would like to do, what would be very nice, is to link these two programs together into something that implements both F1 and F2 and makes no remaining external calls. So we want to dispatch the calls inside the program so that everything is resolved. And so what this means is that we want some link prog operator that gives us a closed program of this of some language. But this language cannot be L1 or L2 because now we are mixing code of two different languages. So what we do is we do exactly this. We define a new language which corresponds to the linking of two other existing languages. So link-lang is a language for linking of L1 and L2. And then we have this link prog operator, which takes two programs of language L1 and language L2 and gives us a program of this link language. And intuitively, the idea is that now execution of a link prog is just going to take these two underlying programs and run them one and the other and just dispatch the calls between the two. So one is making an external call implemented by the other, is going to run the code of the other, and so on. So a bit more formally, an expression of this link language is going to be the currently running expression on the left, which is either going to be an expression of language L1 or language L2. And this runs under a stack of evaluation contexts, which interleave context of language L1 and context of language L2. And whenever this expression makes an external call, it's going to take off the context, put it on the stack, resolve the call by running the other function from the other program, implementing the call, and continue. OK. Note that I've cheated a little bit and that I haven't talked about how we can share state between the two languages. This doesn't work as is because the languages have different type of states, but there are some extra stuff so that they can communicate with shared memory. Very good. So, and as you might expect, we have taken our formalizations of mini-C and mini-ML, and they are inhabitants of this language interface. So now can we just link them together? Well, no. This doesn't work because they just operate on different values. They don't really know how to talk to each other at this point. So remember that our link-lang could link languages with the same type of values and actually sort of compatible states. Here, these are not compatible at the moment. And indeed, we have just not defined the FFI semantics, how we can bridge between two languages. So we need to do that. And this is done by defining yet another language, which we call wrap-lang. And wrap-lang here is defined, so it's defined as it has its own language, but essentially it embeds ML-lang. So it embeds the semantics of running ML code, and it adds new semantics for the FFI on top of it. And so this results in a language which inside can run ML code, but is an inhabitant of language with C values. So you can talk to it by calling the C calling convention, and inside it is just going to run ML code. And it's going to use the FFI semantics to translate at the boundary. And indeed, we have this wrap prog function that can take a random ML program and turn it into a program of this wrap-lang language. And intuitively, if you do this, then the program wrap prog E is going to emit the same external calls as E, but then translate it at the boundary to use and receive C values. And then if you are from the outside, you can also call into wrap prog E, and this will implement all the FFI operations. So wrap prog E gives the semantics to the runtime. It equips E with all the OCaml runtime operations. And it also provides a main function that you can call at the top level to just run E. And now that we have this, well, we can combine this stuff to get our full semantics for the entire system, which we call combined lang, which is the linking of the wrap lang and the C language. And we have a combined prog operator, which allows you to take a ML program, a C program, and link them together with the adequate wrapping. All right. And so this is how we structure the system. This was just about semantics. So now we need some reasoning principle at the level of the problem logic to reason about those. And very shortly, these are simply structured around a notion of program triple, which you write like this. And this is basically the equivalent of for triple, but at the level of entire program modules. And it is read as follows. Assuming interface psi, we have proved that program P correctly implements the interface pi. And if you have concrete programs at hand, you can prove this by stepping through the code and using the rules of the program logic. Essentially, you just have to prove a triple for each top-level function of the program. But now the very nice thing is that we can use this to express the correctness of our linking and wrapping operators. And this gives rise to very nice statements, such as correctness of linking, where if you take a program P1, which assumes pi and implement psi, a program P2 that assumes psi and implement pi, so they each assume and implement the stuff that the other implements and assumes. Then you can link them together, and you obtain a program that assumes nothing and implements the two. As an administrative side condition, the program have to contain different functions. Otherwise, there would be some ambiguity. And then for wrapping, this is slightly more hairy, but essentially, if you have an ML expression E that you prove is safe, it's just going to be called by the main function. So in itself, we just have a trivial specification for it, and assumes some interface psi for the C function that is going to call. Then wrapping this expression assumes a wrapped version of psi, which I have not defined here, but essentially just adds this tilde ML relation for inputs and outputs. And this now implements all the primitives of the FFI and this main function that we can call. And so the idea is that if you have an example such as the hashref example before, you will use the rule of the program logic to prove program triples for concrete parts of the program, use these two lemmas to put them together, and you will obtain a statement that tells you that you have a closed program P, a multi-language program, that assumes nothing and implements a top-level main function. And if you do this, then you can apply the adequacy theorem of Melocoton, which tells you that then in the operational semantics, this program is safe to run, which is the criteria that we use to say that we have proved that all is good. And yeah, as usual, this adequacy theorem effectively extracts correctness in the logic into safety in the operational semantics. That doesn't depend on any array stuff. Okay, so let me conclude. Let me conclude with what I've told you so far, the top-level key ideas, what is in Melocoton but I've not told you about, and some plans for the future. So what I've shown is that we give in Melocoton a sort of general recipe for merging two languages. First, you take the languages on each side and abstract over the other side using these external calls and interfaces. Then you need to formalize the semantics of the FFI to define how the languages are going to interact. And in order to bridge memory models at the problem logic level, you can use this view reconciliation technique. Also in Melocoton, but that I have not shown, first, as a sort of technical point, we use angelic non-determinism to define the FFI semantics for the step where you go from a block heap to a high-level heap, because a low-level value does not have a unique representation as a high-level value. So to avoid making a choice, here we use angelic non-determinism. And this in turn requires the use of transparent arrays to have an adequacy statement that works. But yeah. Then we formalize more various aspects of the OCaml FFI. If you are an OCaml programmer, you might have been sort of confused why I haven't talked about all the weird stuff with the GC and the root and so on. We do formalize it. I've just not talked about it. But once we have this setup put in place, it's not that hard to define. We also formalize callbacks where you can invoke an OCaml closure from C code and some limited form of custom blocks. And then something which I think is really nice is that we can leverage the very standard technique in the Iris world for building a semantic typing logical relation for ML types. And we just adapt this a little bit, but this is very easy, for external calls, which are annotated with these ML types, so that now we have verification conditions to say that maybe we have implemented some weird C plus OCaml plus FFI code which use some unsafe stuff, but now we can prove that it obeys some type-safe interface as an OCaml type. And now we can stop proving stuff, because we know automatically that any type-safe OCaml code, OCaml context, that uses this library is going to be safe, because this library implements a type-safe interface. So this is also very nice. It's something that we get almost for free by just using Iris. All right, so some ideas for future work planned and ongoing is to extend this model with remaining features of the FFI that we have not modeled yet. And we have the beginnings of a static analysis tool for FFI glue code. More ideas would be to maybe go and model the multi-core OCaml FFI, if someone is courageous. Turn into maybe try various verification or bug finding or runtime analysis techniques for FFI code, maybe based on the operational semantics or problem logic of Melocoton. Maybe a different approach is to just give up on trying to verify C code and instead build a DSL for writing this FFI glue code, maybe with built-in verification conditions. Or just try to extract reusable bits of this formalization into Iris libraries that other people could use for multi-language problem logic building. I don't know. If any of these sounds interesting, I'm happy to talk about it. And with that, thank you for your attention.
Thanks. Are there any questions? Please go ahead. Armel, do you want to choose the questions? Or?
Yeah, go ahead.
Okay. Yeah. Thank you. You said that for OCaml, the operational semantics of an external code has no semantics, so it gets stacks. Maybe I missed it, but I don't remember you saying what is the operational semantic on the C side.
Right. So yeah, good question. So if we consider just the semantics of one language, so either the OCaml side or the C side, external calls have no meaning, but eventually they are given meaning by this linking and wrapping operators. So in the end, if you just look at the semantics of one language, then external calls do not do anything. But when you combine them, then you consider the semantics of the language plus the linking operator, plus the wrapping operator, and now everything becomes connected with this additional translation done by the wrapping wrapping semantics.
Okay, thank you.
Jean, well, okay. Yeah.
I have a question about that val int in the program that you showed.
Yeah.
I assume on the C side, hash pointer returns a 32-bit integer, but OCaml ints are 31 bits. So what happens with that 1 bit from C?
Let's see. That's a good question. I guess that wouldn't work in that case, yeah. Yes, I am papering over any integer size issue here.
Right.
So the integers that you get from OCaml becomes a 31-bit integer in C.
Right, that one that works.
But then you hash it, and then you get maybe a larger integer.
Right.
Then you are in trouble. Yeah. So the person writing this glue code would have to do some extra work.
Okay.
because I think like val int is going to drop the extra bit.
But could you possibly change the spec of val int so that it says the thing you pass it should be less than 2 to the 31?
Yeah, that should be in the spec of val int. Yeah.
All right.
Yeah.
Cool, thanks.
So I have a couple of questions. So with the way you define sort of individual languages, it seems to be sort of very symmetric. There's no language that is sort of better than the others. But then when you showed how you linked it in the specific case of OCaml and C, it seemed like C had a sort of privileged status.
Mm-hmm.
Is that a general thing, or is that just specifically in this context it was helpful?
Yeah, that's a very good observation. And so, yeah, indeed, as you say, like this picture looks very symmetrical. That's a lie. Yeah, indeed, there is an asymmetry here in that the way the FFI works, at least for OCaml, like in the code, is that linking is done with LD, like the system linkers, and it's a C linking model, as I understand it. So, and also like, so C does not have to know about OCaml. C just produces a C program that gets links into what it's going to assume another C program. On the OCaml side, OCaml has, if you link just OCaml program together, OCaml has its own linking language. And so the OCaml FFI semantics has to know about C so that it can produce something that obeys the C calling convention, the C linking model. So there is really, so this is where the asymmetry comes from, is that the C language also shares a linking model with the platform linker that you use to link these languages together. So as I understand it, this is where the asymmetry comes from. If you were with different languages and different models of linking, things might be different. If you know of example of that, I'm interested. Does that answer the question?
I have a second question.
Mm-hmm.
I hope I'm not stepping on anyone's
Go ahead.
feet. That is kind of related. So at some point you showed this operational semantics that had sort of two heaps, one on the left for ML and one on the right for C. And I was wondering, are they sort of, is there any permeability? Can you move things from the left heap to the right heap and the other way around?
Yeah, so as is written here, no. In practice, yes, a little bit, and probably more when we implement more aspects of the FFI. So what would happen here is that what happens today in the semantics that I have not written here is that whenever you go from the ML heap, so when you do this step, the ML heap is going to be translated into a block heap, but also an extra piece of C heap that you merge into the C memory. This is used for the root right now. And when you go the reverse direction, you take out this piece of the C heap and you use it to produce the ML heap. So right now we have this limited use case, but in the actual OCaml FFI, what you can do is you can have, say, byte arrays, OCaml byte arrays, and pass those to C, and then C can do mem copies in there. And then whenever C returns, then you get updated byte contents as an OCaml value. So we do not model these right now, but it would use the same principle where you have a piece of C heap that can be shared and given to C and then taken back. If?
So the whole point of this formal verification is to catch bugs.
Yes.
And when we looked at this example with integers, there's a possibility of bug.
Mm-hmm.
Where is the catching process happening? At what point is there a leap of faith in description of the whole framework? Where is the mistake? Where can we leave a mistake?
Why did I not catch the val int bug? Yes. The leap of faith is that we define by hand some operational semantics, which we say this is the operational semantics of OCaml and its FFI. So that's sort of ground truth. That's what we define and take as ground truth, and we build the problem logic on top of that. So the problem logic is proved sound on top of our operational semantics. But the operational semantics, we just thought very hard and defined.
Okay.
Yeah, so that's the leap of faith, I would say. But I mean, it's the same leap of, in principle, it's the same leap of faith that you do when you take any iris formalization of, I don't know, like mini-ML, and you start by writing some semantics for mini-ML, and these semantics are just assumed.
The same leap of faith when we say COM-cert C is C.
Exactly, yes.
Yeah, it's a bug in OCaml, right? They didn't verify that val_int preserves all 32 bits according to the spec that we
Yeah, but this is knowledge you have, so this is something we can encode in the description.
Hi, thanks for the talk. And related to the two last questions, so would it be possible to verify the FFI implementations with that framework or another one?
So, I mean, I guess this is a step in that direction, but I don't know how to do it. The way I see it, it amounts to a compiler proof. In some sense, the FFI is the way I see it, the FFI implementation is the output of the OCaml compiler when it takes source OCaml code, which does not know about the GC, has this high-level semantics, and produces low-level code that can now materialize the runtime part that also include the FFI stuff. So I would say that this source-level FFI semantics would have to somehow connect with this compiler proof, but I really don't know how to do it.
Oh, okay. So the inval, the store field, and so on are not like C functions that the compiler calls?
They are mostly written in C. I do see that as an implementation detail because they are written in C, but also the runtime is implemented in C with some bits of assembly. So it's not like there is a clean barrier of abstraction between the code produced by the OCaml compiler and the runtime. Like the code produced by the OCaml compiler outputs some symbols that the runtime hooks into and so on. Mm-hmm. So yeah. So the way I see it is really, okay, this is just a big stuff that is produced by the compiler, and maybe some part is in practice implemented in C once and for all.
Okay.
But yeah, maybe I'm wrong, but that's how I see it.
Yeah, and just one quick question. Mm-hmm. Regarding the two heaps, is it possible that somehow the C heap is not empty when the
what, you mean when the problem starts? Or the C heap can if you do malloc in C, this will create some stuff.
Yeah, but like for example, in your operational semantics, you start in ML, blah blah blah, and then you do the external call, so you have to translate the ML heap into block heap. Mm-hmm. At that point, can the C heap be non-empty before doing the external call or not?
So if you haven't run any C code before, typically it will be empty.
Okay, but if you had done other,
if you have run other C code before, then this might have malloc stuff that you might want to reuse again, and then this is in the C heap.
Okay, so that's why you had two heaps.
Yeah.
Okay.
Yeah.
Okay, thanks.
Thank you.
Very much. And then we get to the next talk of the session, which is about CertiCoq WASM.
Does the sound work? Cool. So Amel talked about something very ambitious and exciting, and this is going to have a very different programming programming language semantics and Coq are awesome, and how they can have an impact on the real world. So in a sense, everything is in the title, even the first line of the title. CertiCoq wasn't. That's it. Maybe I'll talk a little bit more about it. So this is joint work mostly by Wolfgang Meyer, who is a master student, and then us. And if the title wasn't enough of a short summary, here is another short summary. So we have a way to turn Coq programs into WebAssembly programs, and it's verified. If I had wanted to be whimsical, I could even have put like another cockerel up there. So I won't run a demo because I've been scared with all the AV problems. But basically, the way you use CertiCoq WASM is you write your Coq program. For example, here, this definition foo, where you run super exciting mapping of odd onto some numbers. And they would like, but I would like to run this fast. So I'll just use CertiCoq to extract WebAssembly code into this foo file, and then I will call node.js, as part of my verified infrastructure, to run this very fast. Or at least, this is the whimsical version. The serious version is you take your Coq program, you extract it to WebAssembly, and then you can benefit from 50 engineers who full-time worked on tiered JITs that will run your code super fast. So, if you have a big Coq development, then from time to time you might want to test things or to see, does this evaluate to what I think it should? And this provides a reasonable means to do it. So for example, here, you can check that this is actually what you expect at the end. And indeed, is 1 odd? Yeah, I think so. So that matches what I would expect. So I've verified that at least this specific thing does what I expect. OK. So how does it look like inside? So what we've done is basically we've taken CertiCoq and we've hijacked it. So CertiCoq starts from Galena over there, uses Metacoq to get a deeply embedded term, and then does a whole bunch of very clever things to defunctionalize in CPS and God knows what, and do a whole bunch of optimizations. And we don't need to think about these. These have been done by someone else. These have been very nicely encapsulated to generate this lambda ANF terms. And then what we've did is just compile these to WebAssembly and then prove that this compilation is correct. And this was, it's a very nice thing that it just works, that we were just able to take it off the shelf and use it. So now I'll just ramble more about these things. So I'll talk quickly about WebAssembly and why it's nice. I'll talk about CertiCoq and this rather low language inside of CertiCoq that we start from. I'll describe quickly the backend and then some evaluation, because the whole point is it kind of goes a little bit fast. So WebAssembly. What is WebAssembly? It's the promise of almost native performance with secure sandboxing. So you can run a program that someone else has written, and it won't destroy all of your data. And one of the very nice things is that it has a simple and clear semantics, because PL people have gone out into industry and sort of pushed for simple, clear, unambiguous, the program will run the same on every single machine semantics. And surprisingly enough, people have listened. It's supported by every major browser, and the same program will run the same everywhere. And this means that you can take your Rust program, your C program, and you don't have to worry about how the hell it's going to be compiled on that platform or that platform. You just compile it to WebAssembly, ship it, and it will run. And it's been very successful on the web with the whole Web3 and blockchain buzzwords. But there's also just normally running normal applications on a browser, and also outside of the browser. So there's standalone runtimes, and WebAssembly, it started with the web, but the web is a bit of a misnomer these days. It's really a general thing. And because it was designed by PL people who knew what they were doing and who really cared about having a precise language, we have a complete specification of the 1.0 standard. It's word for word, but in Isabelle or in Coq, depending which proof assistant you favor. In this room, it might be slightly biased to the right. But the thing is, this is a real language standard that is really used in industry, and we have a complete Coq formalization of it. So, you know, it's a huge success story, and the fact that we were able to use it as a target is really very nice. So what does WebAssembly look like in practice? It looks like this. It's a simple stack language where you define modules. Modules are the sort of unit of shipping code. And then a module can have some global state here, some constant that is initially 41. And then you can define functions. So it's sort of structured. The assembly is a bit of a misnomer. It's something that is easy to generate assembly from, but it still has functions. It still has structured control flow. And then inside of the function is just a simple stack language. So it does exactly what you expect, you know. Const pushes a constant on the stack, and there's no catch. You know, it's not like C. This is actually literally just pushing the constant 1 on the stack. And then the operational semantics, well, this is a little bit of a lie, but it's barely a lie. It's what you would expect, just there's a little bit more details. So there's something about calling the host, which is, I guess, the FFI aspect. I won't talk about that. And then there's a store, which is literally, you know, it's a store like you would expect. So a local variable has a value. There's no tricks. There's no catch. There's memory. Memory is just a list of bytes, and this is what we will use to store the constructors of our Coq term. And then the list of instruction is a stack. It just works like a stack. So everything is completely as expected. So for example, if you have your program here that we had inside our function that starts by pushing the constant 1 on the stack and then gets local variable 0, then, you know, there's just, like, if you look at the standard, there are named rules of the operational semantics, and these are the thing that the web browser implementers pay attention to. So it's exactly like a PL textbook, but it also runs in your browser. So now maybe a quick word about CertiCoq itself. So what we do, as I said, is we take this lambda ANF language and we extract WebAssembly from it. And so it means that sort of from the deep embedding down to WebAssembly, this is completely verified. Original CertiCoq from lambda ANF generated C-Lite. And I think the proof is sort of almost there, but not quite 100% there. Maybe someone in the audience can correct me since I last checked. So we have, as far as I know, this is the first verified compiler to WebAssembly. What does lambda ANF look like? It's a relatively simple lambda calculus, exactly as you'd expect, where you have constructors that takes a bunch of arguments and then pattern matching. And this is basically, you know, if you have successor of something, well, you will just have your successor here. And then if you have some destruct on that, then this will be this case construction. So it's a very simple language. It's very pleasing to work with. Like, it's very nice that CertiCoq has this nice factorization through this. You have a language with variables that are globally unique, so it's easy to compile. There's no primitives. Everything is in CPS, so calls are easy to compile. And the function definitions are pulled out to the outside, so there's none of the nasty Coq nesting. So in a sense, it's very easy to generate WebAssembly code, and this is what we used. So how does our part of the compiler work? So it's basically what Wolfgang did is he looked at the CertiCoq C backend, and he looked at the WebAssembly specification, and he sort of tried to marry the two. And it works just in the way you'd expect. So you have a code-gen function that takes an expression and just recursively builds a WebAssembly program. And because WebAssembly is nice, this just works out of the box. And then you do that for all the functions one by one. And you also generate a few helper things to, like, typically you want to look at the output of your function. So there's something that converts the representation in the heap of a Coq term translate it to lambda ANF, and just prints the S expression. This is what we used earlier to look at the result. And then there's something like you need to store the result somewhere. You can run out of memory in WebAssembly, so you need a little point, like a little flag for that. But apart from that, it's really, you just take the lambda ANF term and you lay it out in the heap with a tag and then the arguments just in the bytes after that. And again, as Ahmed said, you're supposed to show Coq code. So this is the Coq code for the compilation of the projection in lambda ANF. And basically, if you're taking the projection of something, well, you just compile that thing, and then you look up. So you need to do a little bit of arithmetic. So you need to skip the tag and look at which bytes correspond to the thing that you're projecting. But because the memory in WebAssembly is just a flat array, there's no complicated things like in C. It's just arithmetic. So you just need to check that this does the right thing. And then you can try to prove it. So the correctness statement is if you have in Coq some expression that reduces to V, and our compilation function returns an OCaml, sorry, not an OCaml, a WebAssembly module, then WebAssembly says this little extra step, which is called instantiation, which takes a module which is a sort of static object and produces what is called a store, which is a bit of a confusing name, which is a sort of dynamic state. So you need not just compilation, but instantiation to succeed. Then basically you can run the WebAssembly program, and this is this formal definition of the semantics of WebAssembly. And then if you get an empty stack, then you've terminated, and then the globals in the WebAssembly state sort of are a representation of the value V that you expect at the Coq level. Or you were unlucky, and then you run out of memory. And this is relatively, I mean, there's a few side conditions. The variables in E need to be unique. This is easy to implement. The size of everything has to fit in I32s. Otherwise, compilation would need to add. I mean, you don't want to have bigins for everything. So, you know, if you defined like, I don't know, 2 to the 64 plus 2 constructors in Coq, then it would be kind of annoying, and we just ignore that. We say, well, no one will do that, and if they do, it's their problem. And there's a few side conditions, but these are very minor. And then the idea of how do you represent lambda ANF / Coq value in WebAssembly is kind of the obvious thing, except, you know, there's details everywhere. So there's things like, you know, you have to think about offsets in memory, but fundamentally it's doing exactly what you would expect. And the proof is like in a PL textbook. It's by induction on the evaluation derivation. And you just make sure that the thing goes pretty much in lockstep. And you need to define this relation that is, you know, what does it mean to lay an entire lambda ANF term in memory? But it does kind of the obvious thing. I keep saying that, but it shouldn't be seen as a negative thing. The fact that it's obvious is so nice. It's so good. Like, it's such a difference to working with other languages. And then we can think, OK, so now we have this thing. We have this compiler. We know that it's correct, but is it any good? And here I'll so it's, you know, the compiler itself is like under 500 lines of code. It's very, very nice. You know, it's and the correctness proof is not that long. And then we've ran it. So it's a small compiler. It doesn't try to be very clever, but at least it's verified. And then we've tried it on a few benchmarks that CertiCoq used for itself. So they have this SHA function, which is quite numerically intensive, and they have some decision procedure for separation logic, I think. And I am now discovering this slide at the same time as you are, because Wolfgang ran it slightly faster this morning, and then I bravely pulled his changes to the slides. So if we compare, so this is CertiCoq itself, which generates C. and if you run it with GCC minus O2, which is very unverified, it's like, let's pick the first example. There's like 7 milliseconds for C, and our thing is 81 milliseconds. So it's like roughly 10 times slower, something like that. This is not a very scientific evaluation. It's just a back of the envelope thing. So it's like, it's not as good as C, but it's still pretty good. And this is after spending not too much time trying to optimize the hell out of everything. We suspect that it can be made even faster. So this is like, it's a very simple compiler, it's verified correct, and it still gives us reasonable performance. So to conclude, I'll maybe talk about the limitations a little bit. There was this step about instantiation that I kind of skipped. We think that we could also prove that instantiation just goes through. We haven't done it yet. I think the big problems right now are sort of performance. Performance both in terms of time that I've just mentioned, but also in terms of memory. So currently, we don't attempt to do any form of garbage collection. So the heap just keeps accumulating old lambda ANF terms that have by now been completely discarded. Logically, but not physically in the heap. One thing that would be kind of nice would be to support sort of primitive types. So currently, if you want to add the number 7 and the number 4, then you need to represent 7 as this giant linked list in the heap, and then 4 as this giant linked list, and then walk over them. And that is kind of completely inefficient. And so we're thinking, how could we try to use like the primitive types of WebAssembly to do if we know the bounds on the integers, or if we don't, at least use an efficient big int representation as opposed to like the world's worst representation of integers. WebAssembly, the 1.0 spec didn't have tail calls, but it's just a question of once you've generated the binary, you can do this untrusted step of replacing call by tail call. We don't have a formalization of that, but we expect it should be relatively doable. We just don't have it in our formalization. And CertiCoq has several types of terms it can generate, and currently we only support a specific one, but I imagine we could do something slightly nicer. So to conclude, we have a verified WebAssembly backend for CertiCoq. It runs with like okay-ish performance. You can grab it off the internet at this address, and then in the future we'll try to think about GCing and performance. I'm happy to take questions.
Thanks. I think we have some minutes for questions.
Thanks. So I was wondering, on that one slide, you had a fun little footnote saying one benchmark crashed what to WASM or whatever, something that is, some graph coloring something, because of file size. How big was that file and why was it so big?
It was quite big. I think, I don't remember how big, but it was like maybe a couple of megabytes, something like that. Something like you wouldn't really, I don't think, yeah, it wasn't really a sort of very normal program to write. And I don't remember exactly why it was so weird.
Oh, but a couple megabyte binary doesn't seem so terrible either. But okay. Maybe I'm just desensitized by Rust.
I don't remember the details, but I think with loads of these tools, they're sort of, they are designed to handle a specific, you know, they only make it handle the things that they encounter, and I guess this was just a weird program from their perspective. Yeah.
Thanks.
Just a quick observation, because Wolfgang pushed the statistics at 5 in the morning this morning. So could you go back to the slides for the tables?
Yes.
So precisely where you have the cursor, we're actually faster than ComCert on one of the statistics. So I was quite proud that Wolfgang actually achieved this.
I mean, it shows the benefits of, tiered GCs written by hundreds of Google engineers. Not GCs, JITs.
Thanks.
So to add a GC, if you go the route of using the native WASM GC, which seems maybe the easiest option, do you think it would change your compilation path and code a lot, or do you think it would be like an easy change?
I imagine from the point of view of our compiler, it would change very little. The problem is you would need to change the our formalization of the WebAssembly specification to handle the GC, and currently we haven't looked at that. I think this is one of the challenges with WebAssembly is that the spec is, people are very keen to add things to it, very, very keen. And it's difficult to keep up.
In this slide, in the performance evaluation, the two versions that you see do have GC, whereas yours doesn't, so you're comparing different things?
Yes, that is correct.
And do you have any idea how much they pay for freeing memory?
No. This is a good point. As I said, it's a very back of the envelope. We haven't done much work on performance, so we're comparing apples and oranges in any case.
Hi, thanks for the nice talk. I was wondering, I mean, there's a lot of very weird things in the Coq front end, and some of them are supported in Metacoq, some of them are not really supported yet. So I was wondering what kind of nasty things are supported all the way down to WebAssembly, things like, I don't know, co-inductive types or primitive types, or this kind of nasty beasts.
That question is well above my pay grade. You should ask the Metacoq people.
Yeah, I mean that's why I'm asking, because I know, I mean, I'm from the Metacoq people, so I know what I know what no, so I know what crazy things we support, but I was kind of wondering if you knew how much of them are supported all the way down through CertiCoq, or whether CertiCoq has to kind of restrict some of the things.
I think there is Mathieu who's raising his hand over there, so maybe he can answer.
I'll ask him then.
No, maybe he should answer.
Or maybe he can answer it.
Wait, I think there's a microphone coming your way.
The primitive types are primitive values are translated down to CertiCoq and down to lambda NF, but not operations. We don't do anything special about int add, for example, for int63 primitives. So you have to implement it in C or in WebAssembly as a FFI library, and there's no proofs about it. And co-fix points are not translated to down to lambda NF. We tried one naive implementation, translation of fixed point down to co-fix points to fixed point. It was a very naive one that copies stuff all the time. But its proof is not so easy, so it was not integrated in the verify pipeline. And the rest of Coq is translated.
I think one of the nice things is because we sort of hijack the CertiCoq pipeline so low that whatever will be done for C, we will sort of inherit for free, I expect.
Do you have an estimate of the size of this project in terms of man-months?
In terms of man-months? 10 ECTS. Yes, 10 ECTS. Which is literally a number of hours by EU regulations. By law, it is a number of hours.
Yeah, but 10 ECTS for how many people?
One.
One, okay.
Well, because ECTS are hours, they are fungible between people. There you go. Formal semantics of EU regulation. Oh, I think Ralph said how many hours? 30 hours for one ECTS. So you could use a CertiCoq WASM to run this multiplication efficiently.
Let's thank Jean again. And we will continue it at 11.
Could you guys please go up to Viv
touch this bit because it makes a big noise in the recording, but you can't hear it in the room.
I try.
And then, yeah, that mark is for the rest of you to share.
Okay, yeah. I don't think I will say anything, but
yeah, me neither, so there's not.
Just in case, but that's it. Thank you. I know still a little change in languages. As if là, ouais. Parce qu'il y avait pas de dire, c'est ça.
Bon, il n'est pas obligé de rester sur scène peut-être au début, hein, c'est pas, je sais pas.
I'll make it clear. I know. I'll state my case, of which I'm certain.
Maybe we should do a concert.
Bravo,
C'est vrai qu'on avait 30 minutes, on avait 90 minutes, on avait tout le temps de faire un concert. Hein.
On a 90 minutes. Waouh.
Tu aurais dû me laisser prendre la guitare, t'avais pris la trompette.
Non, mais là, cette fois-ci, j'ai décidé de voyager les
Je pouvais faire la batterie.
Et maintenant,
Si, sûrement.
Hola.
All right, welcome back. So this is the highly anticipated Coq developer session, which unusually this year we're having it in the middle to accommodate the speakers. So Matu has graciously agreed to give the usual short presentation on recent features in Coq, recent developments. And then we'll have most of the session time devoted to audience questions. So I think what we'll do is we'll have Matu start with the talk, and then we'll have the panelists introduce themselves and then get on with audience questions. So yeah, take it away.
Thank you. Okay, so a few news. So the outline of my presentation, I'm going to talk about kind of a mix of all the main visible features that have been added to Coq 8.17, 18, and 19. A little bit about the Coq platform, things about the Coq future and the roadmaps, and then a highlight two kind of developments, I mean large developments
that you should know about. And then we'll have the usual Q&A. Okay. So this last year, we released quite a bunch of Coq versions, starting with 8.17 around January and March 2023. There was a platform released in January, actually, also for the previous 8.16 version. We have point releases that are regularly released, and also release candidates that I encourage people to try, because we kind of like to have the feedback on these versions. So it was quite a busy year, but as you can see, we have a pretty well thought out release process now, and we are able to release as we go. Okay, just the platform might be a bit late. It's a large project to have Coq installable on a Mac OS or on Linux or Windows with a bunch of libraries and a coherent set of libraries. I'm going to talk about it a bit later. But of course, it takes time to develop this and to maintain this. Okay, so a quick overview of some of the features you can find in 8.19 that were released throughout this year. There's been a lot of work on notations, allowing to activate and deactivate them locally. I'm going to demo that. There's been work also on scopes, so the syntactic scope that you can assign for parsing. I'm going to demonstrate that as well. A lot of work has gone into improving LTAC2 so that it could actually replace LTAC implementations. So there is a way already to interoperate between LTAC2 and LTAC1 if you want to port your developments. And there are much richer APIs now for developing with LTAC2. And a nicer programming interface in the sense of a case compiler, for example, to write deep pattern matchings on LTAC2 values, and a lot of bug fixes. The main new features from the kernel point of view is sort polymorphism, which was just introduced in 8.19. And basically, the idea is that you can generically define some things that will work over prop, sprop type, or whatever new sort we add in the future. And finally, there have been a lot of standard library improvements around arithmetic libraries, lists, and analysis, so real number library. I'm not going to go over that, but you can look at it in the changes. Okay, so a little demo. Let's see. Okay. So as you probably all know, you can have notations in Coq. Here I'm using as a notation for natural number addition. But there was no way before to disable a notation at some point in your development. Now you can do that, but of course, notations are overloaded, so you might have multiple definitions of the same notation that are interpreted as different things. So for example, plus is also a notation for the sum type in the type scope. Yes, I can do it larger. Okay. So when you want to disable a notation, you need to either say I want to disable all the interpretations of the addition or some specific ones by specifying, for example, here, that I want to disable just the notation for addition on natural numbers. And then it's no longer available as an interpretation when we type check terms. Okay. I can also disable all the notations. And so the notations are still there, so just not used for interpretation. So it's not a way to fix the problem of incompatible notations in different libraries, in the sense that the parser is still extended with the notations. They have just disabled interpretations. Okay, so I'm going to re-enable that. And you can also disable abbreviations, which are special notations which start with an identifier, which is treated specially and do not need those ones to modify the parser. Okay. Temporary scopes. Maybe you've noticed that the scoping annotation that we have in notations here says that P has to be interpreted in the type scope and all its subterms as well. And the temporary scopes allow to use the notation scopes just at the top level of the parsing. So in particular, this prevents to use the same notation for different meanings in the same expression. For example, here I'm using the conjunction of application of the P predicate and the Q predicate. But in P, I'm also using a multiplication on natural numbers. And this cannot type check because here the star is interpreted as a type star and X is not a type. Okay, so if you use this syntax with this underscore, it says that I'm going to use the scope just at the top level, and then everything works out nicely. And it's probably the default should have been this temporary scopes at the introduction of scopes, but now you can use it using this underscore scope. And there is a plan to actually make it the default in arguments and in notations in the future, to switch the meaning of the underscore and the non-underscore one. Hmm? Yes. Can you repeat the question? Oh, sorry. Yeah, the syntax for the new scope annotation is with underscore and your scope. Yeah. Okay. Something that was actually not introduced in 8.17, but before in 8.16, it was improved on after, is the ability to do selective imports. I don't know if people are aware that this is something that you can do. So when you import something from a library or a module, you can give the set of names that you actually want to have available unqualified, and the other names are just going to be available, but with qualification. So typically, if I import some lemma from a library in Coq, and I select just the NNPP lemma here, then I don't get access to the classic axioms, which is part of this file. But I can always have access to it in a qualified way. And I just get the unqualified version for the lemmas I selected. And you have import categories available. So you can say, oh, I just want to import the coercions, hints, canonical structures, notations from this library, but not the rest. Okay. So on the way to implement sort polymorphism, we first introduced a generalization in the way we do type inference, so that we do not commit to the type sort too early when we elaborate. So typically, when we write this statement in previous versions of Coq, it would assume that P is a type, and come to this point of the expression and find out that actually P should have been of type prop, but it's too late at this point to change the type of what was guessed for the binder P. So this is no longer the case. We have a notion of sort variable during unification that allows us to defer this choice. Okay, and that's something that as a newcomer to Coq you might find a bit disturbing when you get these errors as a newcomer.
In what version is this introduced?
8.18, I think. So sort polymorphism, it's an extension of universe polymorphism, where instead of just being able to bind the universe levels of some expressions, you can also bind these sort qualities. So the sort qualities are going to be prop, S-prop, or type. So here I'm writing a polymorphic identity function that's parameterized by a sort. It takes a type A in this sort and returns a function from A to A. Okay. So now I can have instances of my identity function at prop, which will have type for A prop A to A, at set, or rather at type 0, if you like. So set is really just a synonym for type 0 now. And at arbitrary types. Okay, so this can be useful to avoid duplication of inductive types, although it's not entirely clear how we will deal with the different sorts for inductive types in general. So right now there is a simple version that is implemented, is 8.19, but we will need more experience with the system to see how we develop. But still, I can define a few inductive types generically, like the empty type, which can live in any sort, and get the notion of false, which is the empty type in prop, and the empty set from this definition generically. Okay. Maybe more interestingly, I can do a polymorphic product and get the conjunction in prop or the conjunction in type from it, and write generic lemmas that will apply to all the notion of products that I have. Okay, so here I'm defining, oops, it's a bit small. I'm defining equivalence of two types as a product of a function from A to B and a function from B to A. Okay, and I can write generic lemmas on this. All the system is adapted so that you can work with that. So there's a bit of trickery here to deal with universes, as you can see. We'll come back to that. Okay. So this gives us, of course, the three instances of this proof of equivalence for prop, S prop, and type. And this works correctly with the elimination restrictions, I should mention. If you instantiate some inductive type as prop, you might have restrictions on the eliminations, and this is accounted for in the kernel. Okay, finally, a bit of advertisement for Altec 2. So in these versions, a lot of new data structures and APIs were introduced. In particular, we have arrays, or mutable arrays, that you can use to program your tactics with a fairly large API. Okay, and we also have a library for maps and set on some subset of possible key types. In particular, you have integers, constants, inductive. So if you want to build maps from inductive names to something, you have this available directly in Altec. Okay, I'm not going to go through the example in particular, but it works. And finally, as I mentioned, at the beginning, the match construct of Altec 2 was a bit primitive. You only had one-level matches, basically. But it's been extended to support nested matching and as clauses with an efficient case compilation algorithm. Okay, any questions? No. Yeah.
So about the universes, in the example that you had quite a bit of annotations. Are they actually necessary?
You mean this one? Let me remember. You can always, well, you don't have to put them in, for sure. It works just as well. But then what?
For the lemma, yes, and for the declaration, for the definition up there.
Ah, you mean for the definition of the inductive type?
Yeah.
If I don't quantify on the sort here, I don't know. Let's try. Then I can do this. A priori, it's just going to be backward compatible. It will just mean that we have products in type and not any sort, right?
Okay, so it's not generalized automatically?
No, the sort are not generalized automatically. Yeah.
So then this relates to the second question. Does this replace, or is it planned to replace template polymorphism?
Yes, that's the goal. Yeah.
But not yet.
Not yet.
Because you cannot generalize yet. Okay.
Yeah.
Thanks.
Any other question on the demo?
can you disable notations only for printing, or all notations, only all notations? Like, can you say, I still want to accept 0 plus 1, but I don't want it to print as 0 plus 1?
I did not play with the system enough to do that, but I think, yeah, it's pretty flexible in that respect.
Okay.
Yeah.
Thank you. A bit silly question, but if I want to define a short command that disables, say, 23 notations, can I do this? And
I mean,
more generally, commands are something that you cannot include inside a tactic, and this seems really painful. I don't know if something can be done about that.
Yeah, you should put them all in the same scope, I guess, to do that easily. If you import a module that disables all notations? Yes. Then what? Yeah. You can write it once and import it multiple times.
Oh, that was related to my question. If I define a module, and within this module, for some specific use cases, I disable notations from a specific scope, if I import this module, will it disable the notations as well? And if so, does removing the notation import category stop the module I import from disabling these notations in the future?
Probably. You will have to play with it.
Okay.
I would guess it like that. I'm not sure. I think notations support local and global and export. But you have I think so, yes. Yeah. Yves?
I have to say that there has been discussions about the developments being not robust to imports. And so a lot of the design that is happening around imports and the possibility to say you want to import only few things and things like that is part of an effort to decrease this amount of fragileness. Yeah.
Clément.
I suppose it's a secondary question, but why is there a space between the pipe and the curly brace on the right but not on the left? Is that because at curly brace pipe is a token on the left but not on the right?
You mean, can I do that?
Yes.
Yes, I can do that.
All right. Great. I think it looks much better.
But there is a parsing ambiguity because of this these pipes, indeed. Let's move on? Okay. Okay, so apart from this, a few other changes that you want to be aware of. Well, you're going to be aware, if you've not been through that yet, that default localities for hints and instances are changing, in particular so that people are aware of where things are exported. So you're going to get a lot of warnings for that. There is some improved control over warnings that should allow you to use warnings to deprecate definitions or libraries more easily. Finally, lazy, simple CBN, eval, so the reduction tactics can do head reduction and not only strong reduction, which is a common user request. There's been the addition of precise profiling support for performance profiling of Coq code. So Emilio is more aware than me of what this actually means in practice. But OCaml5 compatibility, you can compile Coq with it, you can run it, but there's been some performance issues that are being worked on, and the main problem you can have is that native compilation is no longer available, for now at least. Okay, so a bit about the platform. As I mentioned, it's a coherent distribution of the Coq packages with binary installers for standard platforms. It's customizable, so you have a set of scripts that you can customize to do your own variant of the platform for a lecture, for example, or if you want to add a specific version of some development. And it's gonna build all this for you. There's a charter that explain what are the criteria for being in platform and what we expect from package authors. It's been maintained by Michael Sochtrup, and no Romain Teclet, who is here. He's helping with the maintenance of this, which is quite a bit of work. And we've added an editorial board for the inclusion of packages, of which I and Yves are here, I think. Right, so what it's like in, I mean, the last stable release was on 8.17, and there's a new one about 8.18 that is in draft mode, but it's usable for 8.18, yes. As you can see, there's quite a bit of packages. About 50 packages are included. You're welcome to submit yours if you think you have a package that is of general usage. Okay. So about the future, we have a big feature that's coming very soon to Coq, which is the addition of rewrite rules that was implemented by Yann Leray, Theo Winterhalter, and Gaëtan Gilbert mainly. That follows up on more theoretical work by Theo and co-authors. So you will have the ability to introduce symbols, so axioms, which have specific computational behavior by specifying the rewrite rules associated to them. Again, a little bit like with OCaml5, a caveat is that we are not going to support as a native compilation and the VM compilation yet, because you need to really extend them to support the rewrite matching and stuff like this. It's not been done yet. We hope to also generalize this use of third polymorphism in the stdlib to have more generic definitions and less duplication. In particular, we hope that we could have just one instance of the morphisms library for setoid rewriting, which currently have a duplication for prob and type. On my part, I've been working on extending the universe system of Coq so that we can have algebraic universes everywhere. So that means that in the example I've shown, I've added constraint to say that U and V were smaller than the universe K. It's just because we have limitations in the way we handle universes that prevent us from saying just K is the maximum of U and V. And that's the goal of this work. And it should both simplify the user interface for working with universes in the sense that you can annotate precisely without having to introduce these constraints that come a bit out of nowhere. Yes. The work on LTAC2 will continue also to make it a real replacement for LTAC1, and that work that's mainly being done by Gaëtan Gilbert and Pierre-Marie Pedro. And we hope also to integrate the verified extraction pipelines that have been developed. So we've seen a CertiCoq WebAssembly this morning. These things can be used as alternatives to the current extraction to OCaml. I'll come back to that. And you can have a look at the short-term roadmap for Coq, which we hope to continue updating in the future for news on what's coming to the system. If you want to give us feedback, it's very welcome. So the big elephant in the room, the renaming. So you've probably seen on Twitter a few weeks ago, or 2 weeks ago, that indeed on our roadmap it is written that we will rename. the Coq proof assistant into the ROC interactive theorem prover, which you can abbreviate the ROC prover or simply ROC. It's coming from a long discussion. We asked during the last survey users to express their opinions on the renaming and what names they would like. Of course, the result is split. Some people hate the idea that we rename, some people love it. But the majority was either for the renaming or neutral. And in the development team, the majority was for renaming. And the ROC name was actually proposed by Clément, I think. It's going to be pronounced like rock and roll. It pays homage to Rocancourt, which was the birthplace of Coq. And of course, it suggests rock-solid software. So the plan is to make the renaming effective this year with an updated visual identity, website, and the first release. So in the meantime, please still keep using the Coq name until we have something you can really point to. And we are aware that there is a programming language being developed that's named ROC, and the converse is true as well. They know that we are renaming to ROC, and it's going to be fine. Of course, you can, if you need to disambiguate, you can always qualify ROC prover, ROC ITP, if there is an ambiguity. A bit above the longer-term vision. So we're going to continue to implement, to develop this ROC interactive theorem prover collaboratively with some focus on genericity, with building on work on sort polymorphism, rewrite rules, and the many meta languages that you have available. We hope to introduce new sorts that allow you to work in different variants of type theory for effectful computation or erasable data. Maybe some new sorts will come up as well. We are really keen on integrating ideas from observational type theory, which is a variant of type theory which supports natively the uniqueness of identity proofs, functionality, extensionality, and quotient types, which are very common axioms that people have to use or are used to add in their developments to just reason on programs. And it should not be the case that you need to add axioms to do this. We are going to still focus on enabling as efficient as possible embedded domain-specific logics that are iris. And we're also working on providing transfer tools between developments. Of course, we're going to continue supporting the wide array of developments that we have today in Coq. We're going to also focus on robustness. We already have a kernel that's really fine-tuned for performance, but we have less correctness guarantees. So we want to increase that, in particular continuing on the Metacoq project. And finally, there's a big part also on focusing on accessibility and productivity, bringing work to students and engineers. In particular, there are intensive efforts on user interface development, and you'll see talk by Romain and Emilio this afternoon about this. And we need strong automation tools and library management support, and for that we also need support from the community to develop this. Planned events about Coq, so there will be a workshop in Tbilisi in Georgia, and there's a usual Coq users and developers workshop where power users or people interested in development of plugins can meet with developers which are interested in collaborating on some implementations. So this is going to happen in the summer. We don't know where yet. Okay, so some highlights of recent developments around Coq. I'd like to highlight the Coq-LP meta language, which is an embedded interpreter for Lambda Prolog that allows you to write Coq terms, call unification, and do things like that. That's a nice tutorial by Enrico Tassi on this. On top of this meta language, there is this hierarchy builder, which is a plugin that allows you to declaratively state how you want to build a hierarchy of mathematical structures or computer science structures, like categories. And from that, it generates all the definitions, notations, and tools that you need to work with that hierarchy using the methodology of packed classes of Metacoq. And this has been used and integrated in the Metacoq library as a way to produce the structures. Also implemented in Coq-LP is Tract, which is an extensible framework for transfer between theories, which are not necessarily isomorphic, so think integers and natural numbers. When you have an automation tactic, for example, on integers, it will not work on your type of natural numbers. You need a transfer theorem, and this is something that automates that process. And there is an ERC led by Asim Aboubi, which is really concentrating on this subject of automation. Okay. Finally, there is a LibreBassi project, which is about using Coq for teaching, where they are revisiting elaboration phases for natural mathematical expression, for example, fine-tuning type classes and canonical structures. And this is led by Yves Berthaud. So if you have questions, Yves can answer them. And last highlight, shameless plug from me. We have now this verified erasing compilation pipeline from Galena through Lambda Box to C through this CertiCoq project. So it sees that you can compile either Reconcert but also other compilers. What happened for CertiCoq recently is that I made a beta release, and we have a bootstrappable CertiCoq, in the sense CertiCoq can compile itself. There's a verified GC, of course. There's been work on being able to link code that you verify in C with code that is produced by CertiCoq. So there's this VeriFFI project that allows you to do that. And you've seen this morning, that's also a WebAssembly target. We've been also working on building a kind of alternative to the current extraction of Coq, which targets OCaml. But to target OCaml, it introduces a lot of that magic casts. So we've tried to do a correct compilation from Coq to not OCaml but malfunction, which represents the first untyped language of the OCaml compiler for us. You can read about it. And there's also as targets of this some web and smart contract languages like Liquidity and Elm. That this has been part of the Concert project by Daniel Enkoff, and Bas Peters is also participating in that. And this one uses a type erasure phase, so it provides some interfaces in the functional languages for the functions you erase, which is not possible in general, but for some subset of Coq programs which have easy translations to the target, this is possible. And that's it. Do you have questions?
All right, we have lots of time for questions before lunch. Oh, yes, yeah. You should. Please introduce yourselves.
Hi, everybody. This is Emilio Jesus Gallego Arias, and I'm a researcher at INRIA. And my main interest these days is on user interfaces and theorem proving.
Hello, my name is Yves Berthaud. I'm a senior research scientist at INRIA. I've been using Coq for about 30 years. And my main focus right now is on helping the social aspects of the development team and trying to find hiring positions. And so if you are interested in working for the development of Coq, you can talk to me. And I will be involved in the renaming effort. And I've also tried to obtain funding from the INRIA management to work on making Coq more easily usable for teaching purposes, but especially directed at mathematics students' audience. So that was the Liber Abbasi thing that Mathieu was talking about.
So hi, I'm Roman Setli, and I'm the latest recruit by Yves. So I've just been made a permanent research engineer at INRIA, working on user interfaces for Coq and mainly VS Coq. And as Mathieu said earlier, also I've been helping out with the Coq platform, among other things.
He needs to present Mathieu, he was already.
If no one has a question, I have a very superficial question. In the rename, you rename Coq into Rock, and that's good. And also the proof assistant became theorem prover or interactive theorem prover. Why is the second? I like proof assistant, and I'm curious about how you decided to move away from that.
I don't know if I have a very
This is open. I don't want to start another poll to decide that, but I think already now we were able to say Coq prover. I think it's just if you don't want to have an ambiguity with the Rock language, you just have to put something to say that you are using a proof tool of some sort. But then you can use the expression you want. We're not pushing too far on that. We'll use something for the communication, that's for sure. If you really want the word proof assistant to be used, maybe you have to knock at the door at the right time, and that will happen.
So, when I hear theorem prover, I think more of automated theorem prover because it's the common case where we use them. And the fact that what is nice with proof assistant is that people know that they still have to write the proof themselves, and that Coq will help them. So I think it gives a good impression of what the usage of proof assistant is. But I don't mean.
But at the same time, maybe provers should all be interactive. You can think it that way as well. I think that was the point also.
Hello, thank you for news of all the exciting things coming. I'm interested in notations, and specifically what I've noticed over the past few months trying to revamp the notations of software foundations and encountering some difficulties is that there seems to be the documentation of the notation mechanisms in the manual is helpful but doesn't go too far. I think in the community there are various people that have done more advanced things or that understand very well. So there's some latent knowledge. And then there's a set of people like myself that are not necessarily in the set of people that have this latent knowledge, but that want to do reasonably sophisticated things. So I would be interested, first of all, in gauging maybe from a quick poll of the audience, how many people here are like me? They're trying to do somewhat sophisticated things and having trouble. That's kind of what I suspected. So then my second question is, what could we do about making the sets of people that want to do sophisticated things and people that are able to do sophisticated things more overlapping? Is it better documentation? Is it some kind of forum for people to help each other? What is it?
I don't have a right answer. Ask Robert how he does it, maybe.
Well, so what I've discovered is there's basically look in the manual and you find a few hints, and then there's send an email to Hugo or maybe Robert. I would like to have something in the middle. So maybe in terms of direct suggestions, this could be a call for some kind of joint effort, which I would very happily participate in, but maybe could be organized by the ROC team to some kind of community effort to build better documentation or even examples. Annotated examples of fancy things that people have done would be so helpful. So it need not be a gigantic effort, but a little bit would be super.
So my impression is that we already have a very comprehensive effort of documenting things that can be done with Coq, thanks to the Logical Foundation's series of books. But this is not the same level. And but the other thing we have is we have something which is called plugin tutorials, and maybe that should be closer to that level. So this is a good topic to put to the next Coq user and developer workshop, because we could maybe we can start it by a mail or a Zulip chat initiative, but we can try to make sure there will be more critical mass on the topic on the occasion of one of these Coq user and developer workshops. So I'm just noting that down. So just to react to your request.
That would be great. Maybe we could even start assembling a library of slightly annotated examples earlier.
Yeah.
Thank you.
I think in the same vein of like gathering people that do the same thing 10 times in different places in the community, I think there was a discussion on the Coq-Zulip a while back. I think Gregory was on there. I don't know who else was, on trying to unify efforts of people building bits of a universe polymorphic standard library. I think there's a lot of duplication effort on these kind of things now. The standard library is not universe polymorphic currently, but there are a lot of people that need these things. I know there's quite a lot in Metacoq. I've been basically copy-pasting some of it for the Martin of Alacoq thing we presented at CPP, and I think there are other places in the community that do the same. So I think if not know exactly how this should materialize, but I think it would be nice to try and also make these efforts kind of converge, and also maybe try and use the sort polymorphism as well in these kind of things. Would be quite nice, even if probably for performance reasons and backwards compatibility, we will not replace the standard library anytime soon, but at least trying to get into that direction and get something there that others can use would be quite nice. So yeah.
What is the current recommendation on the IDs for Coq? I mean, I have my way to doing. I use proof general, etc. But sometimes the new people ask me to what's recommendation it is. Is it still Coq ID is the official ID which we should recommend to the new users? There's VS Coq, obviously.
So my take on this, and I say my because maybe other people will want to correct that, is that somehow Coq ID should be phased out because it's too much of an effort to maintain. And the solution based on a state-of-the-art programming environment like Code or Codium, VS Code or VS Codium, is the road to go. And we have 2 experiments on the topic right now, and I can't really say, can't really push one over the other. In fact, I should push one over the other because I've been making sure that we hired somebody to work on the topic, and this is Roma. So this is the VS Coq effort, and there's been a lot of effort that should be respected by Emilio on doing the Coq-LSP effort, which is also using the Codium VS Code and VS Codium base. So all this. We want these experiments to well, one of them is not an experiment. It's really I want it to be manned for the long term, and for the other one, I have to understand how to make it more permanent. And so this is I can't give more recommendation than that. The only thing I can say is, in my opinion, the Coq ID effort is going to phase out. For the proof general effort, I can't say anything. I don't know. I don't have a view of the future. I'm myself mostly a proof general user, and I have the impression that it is the only one that provides the level of productivity I'm attached to for now. So I still need to understand and do enough testing about all these, so I don't have any recommendations. But since Emilio and
Mike,
Your mic.
Say that, sorry, that I think Emacs should be supported. I don't see a reason it should not be. Yeah, yeah. So Emacs maybe proof general, a different version of proof general, but should move on, I think.
So, you know, for me, the way I see it, when I said I was doing some sort of social engineering on these topics, I really tried to make an effort that we would have people to man the position on working on user interface. And this is the effort that led to the hiring of Romain. And Romain comes with more of an experience on that topic than an experience on the Coq system. Although he was one of my previous students on Coq anyway. But so we have a sustained effort there. And this is the only thing I can say for this topic. For Proof General, this is not the result of an investment of INRIA. So it's going to live on if the community embraces it. And I think it's the same for Coq-LSP. And I think for Coq IDE, even the community had a hard time embracing it. So that's the reason why. That's my strategic view on it, you know.
Hi. So I'm very happy to see like more movement toward universe and sort polymorphism things, because having the template universes pinned to a fixed universe is an actual source of incompatibilities between real-world libraries. Like we have bug reports in Iris saying I can't import X and Iris because Iris imports SCDPP, which pins list to universe something, and then game over. So I do hope the polymorphization of the standard library will happen, because I don't really see any other way that we can actually compose the different libraries that we are building in the in the Coq ecosystem. And increasingly, we are seeing great compositions of libraries, but the lack of a universal polymorphic standard library is in the way of that. But there's another topic which I would like to bring up, which is my like single biggest pain point working. Like basically every week that I work in Iris in Coq, I run into some issue that I think is caused by unification. Something where I want to write apply, and then I have to write apply colon. I want to write apply in, and then I end up using rewrite because it just works better, even though it's silly to rewrite with an if and only if. I couldn't fail to see that there's no unification mentioned on the roadmap that we saw here. And it's been a topic that obviously has been at CoqPL for 5 years or something at least, I don't know. So I was just wondering what the status of that is, and wanted to just signal boost that this is still a real world problem, and everybody who learns Iris has to learn to just randomly try apply colon and some other things until unification is like happens to be happy.
Okay. So for the it doesn't work, my mic? I have a mic. First part, it should be possible in principle to, once we have this sort polymorphism working well for inductive, to just make the inductives polymorphic in the standard library. So to get away from template polymorphism and to avoid this big one. Yeah, it should be. I don't guarantee it. For the second part, so this uniform effort, the idea that so right now we have 2 unification algorithms in Coq. One is used by the tactic, the vanilla tactics. One is used by typing, so when you enter a definition. And they are kind of incomparable in terms of what choices they make. And the idea of Unifold is to move everything to the one that is used for typing. And it was blocked on this compatibility layer for primitive projections that was introduced when we introduced primitive projections. In Iris, actually. So due to some real backward incompatibilities I would have had introduced to fix it. So right now it seems that we are on a path to solve this primitive projection problem, and then you should be able to go on this project to unify the unifiers. Yes.
Thanks for the update.
Hello. When defining coercions, there's this thing called the uniform inheritance condition, which I ran into recently when trying to make my coercions also work for lists. And when trying to research what was going on, I stumbled upon a bug report that was closed that read to me as if the uniform inheritance condition had been removed, yet there I still was getting warnings. Do you know what's going on there? Has it been removed? Is it going to be removed in future versions? Did I misread something?
My recollection is that it was made optional because it was too restrictive, but maybe we don't have experts on this part here. You should ask on the lip, I guess.
Yeah. Maybe I'll go back to an ecosystem question. So in my own project, I ended up switching from Coq makefiles to Dune. I don't know if I regret yet, but I was wondering what was the opinion of the community on the two different ways of doing a build system for Coq and the fracture that is existing now.
Maybe Emilio can answer this.
Repeat the last sentence, sorry.
I feel that now there are projects that use Dune, projects that use the original Coq makefile way of building project, and there is increasingly a fracture of different projects, and they are mutually compatible, so it's not that bad. But what's the plan? Is there a plan or an opinion of the where it will lead long term?
Well, I don't see that in a position. Is well, I actually we'll talk with Bhakti a bit about build systems today, but. I don't think they're in a position. It's just if you look, for example, this beautiful paper is called Build Systems a la carte. There is a classification of build systems, and actually Make and Dune are really different in the technology they're using, what they can do. So it's a bit what I will say for interfaces too, depending what are your needs. You may have a different choice for a more classical one or a more modern interface. So for example, Make, for example, you cannot even be set soundly with Make. There is a definition of soundness. So I don't think this is a fracture. It's clear to me, like knowing what all the other theorem provers are doing and the way they're hidden, and also knowing industrial scale code bases that we are also handling in Coq with millions of lines, it's clear to me that Make just doesn't cut it. So it's just a matter for the Dune. There is a kind of team working on it, so it's just a matter for Dune to become like the kind of the standard build system for Coq. Of course, if people want to use Make, they can use Make, but I see once Dune is stable, I will see very little reason to use Make. It's just Dune offers you a lot more features. Really, like, I don't know how many hours per week you can save, depending on what are you building. So, depending on the size of your team, I mean, like, so yeah. So it's just Dune was a bit more as an experiment. It's true in Coq. Sometimes we don't. Maybe we should work differently, and actually this is the roadmap. Sometimes Dune, for example, I expected it to be completed in 1 week. Actually, in fact, it could have. Actually, could have, and I understand why. Because actually, but I mean, it's just a different methodology. So yeah, it took way longer than it had to take also because it's a thing. But indeed, like I don't see a lot of Make for whatever people wants to use Make, but really shouldn't be. Most users at some point will find Dune better and easier. I think. I mean, you're free to we are very happy to hear if Dune is not working well for you, what Make is working well for you. That will be. I don't hear many people telling me like I love Make files. I don't actually, but of course, we're very happy to submit a beta testing phase is going to start soon. So then it's still a year for a stable release of this build language.
So you just said people who are happy with Make and not happy with Dune. So I'm still using Make files everywhere. I'm not thrilled with it, but I just legitimately don't know how to set up a Dune Coq project and have everything work. Whereas for Make files, I copy paste the standard PP Make file and everything works beautifully. So I think it is really a matter of documentation.
Do we have a little entry in the reference manual how to set up a project with Dune? So, but yeah, I agree. Like for example, for 1.0 documentation, it's true we didn't spend a lot of time documenting because it's true it's still not 1.0, so things are going to change. But yeah, but I agree, documentation is is one of the big things missing for 1.0. So for now, this was misunderstood. Actually, a problem we have with Dune is interesting. It is clearly marked as an experimental, but because it offers so many advantages to a few users, a lot of people embrace that. The people that need it, actually, or people that discover that. And actually, I started working on that for myself because I was building Coq. First, I started to build Coq, and actually with Make, I was. And in fact, I can tell you, like before Dune, we had like bugs in the build system of Coq, like a couple per month, and since we migrated, we reduced to 0, for example. But yeah, but it's true, like the things were a bit unplanned. Like we weren't expecting so many people to use it, so it got a lot more adoption. This experimental version, that's what we hope.
There has been a change, I think, in Dune 3.8 about how to handle Coq modules and how to specify the dependencies. And it required to update a lot of Dune files to keep up with this change. Will the interfaces be likely to change afterwards and the semantics of Dune files, will the semantics of Dune files change in the future, or will it become stable at some point as well?
Actually, a great property of Dune is that the build language is version. So indeed, once we release the 1.0 language, in theory, we should keep that compatible like for many years.
Okay, right.
So yeah, actually that's pretty useful, though has disadvantages too. But yeah, but in principle, like yeah, you can even try today, depending on the version you put, it's true. Like now we are removing some old versions we discovered that are broken. For example, we didn't realize because we had to do a bit more things. But in principle, a 1.0. Of course, there is the issue if talks about maintenance, but I think like actually it's not very hard to maintain. Was very hard to design, but once the design is fixed, it's very easy to maintain. The code is fairly trivial actually. Of course, the complicated code is by the Dune build system itself. That in Coq we are users of that code. Yeah.
I wanted to just quickly return to my point earlier about notation. I realized that I had phrased my point as a general request to the Coq team to do something, and but there seem to actually be a lot of people here with an interest concretely, and I really do want to see progress in this area, so I don't want to lose the energy that's in the room or the connections between people that are in the room. So, with all of that in mind, I'd like to make a concrete proposal to get started, which is, if you have an example of Coq notations that you feel proud of or that you feel illustrate something that you figured out, could you drop me an email? If you're interested in Coq notations and making them better and how to use them better and want to make sure that you're included in the discussion, could you drop me an email? And I will interface with the Coq team to make sure that some kind of discussion forum / repository / whatever gets created. I'm Benjamin Pierce.
Completely different topic. So one thing you mentioned earlier was LTAC 2. Having done some LTAC hacking last year, I am very much looking forward to never having to do that ever again. So LTAC 1 hacking, I mean. So looking forward to LTAC 2. I think I think there's like something that feels to be a bit missing to me here from the migration path currently, which is the way I view it. Most of our users, Iris users, are using LTAC 1 to write their proof script. And honestly, for writing the stuff between proof and QED, LTAC 1 is like fine. So I don't see a need to push them away from that. But to implement those tactics that we provide to them, we would really like to start to be able to migrate that to LTAC 2. And currently, there's a lot missing on the FFI front between LTAC 1 and LTAC 2. That's kind of what I'm encountering every time I'm trying to just port something to LTAC 2. I think the most recent thing was intro patterns, where we now have this amazing piece of code where we have a list of intro patterns. And so to work with the list, we go from LTAC 1 to LTAC 2, where we can take apart the list. We have a single intro pattern, but then we have to now go back to LTAC to work on the single intro pattern, do something, and then go back to LTAC 2 as we fold. And so we do like a million transitions between LTAC 1 and LTAC 2 as we go over that list, and it's absolutely beautiful, and it works, and it's not a lot of fun. So this is less of a concrete request and more of a, I feel like I've seen on the roadmap things like reporting SS reflect tactics to LTAC2, which seems to be focused on putting the stuff between proof and QED into the LTAC2 universe, which to me personally is the less interesting part. And what's missing to me is looking more into what can we do to make it possible to write our LTAC1 UI, but backend is LTAC2, and to get that more and more into the sane land of LTAC2 and get away from LTAC1. I resist using LTAC2 for a bunch of stuff now, to like have NRE things. I think Tatros, they wrote that. But there's a lot of friction there. And I think mostly it's just APIs missing from LTAC2. And yeah, if there's some way we could make that exchange more productive and kind of reach a fixed point of having sufficiently many APIs, I would be curious for how we can best work with you all on that.
That was Yano. I just tricked him into working on it.
Okay, great. Thanks for doing that.
I think you should contact Gaetan with your requests about the language, and they will be put on the stack. And well, it's more like a priority queue than a stack, but I think we really want to get to a situation where everybody where we can forget about LTAC1. So we need to have the easy usage between proof and QED to be easy enough, and the other part to be to collect everything we can do in a nice way. So let's make sure we don't forget an important functionality. So I think last time I discussed with Gaetan, it was his plan to do a poll on this kind of topic anyway. So you'll probably get an opportunity to speak up.
Yeah, thanks.
I just wanted to say thank you. I'm using Coq mainly on Windows, and this has gotten significantly more painless over the last couple of years. So this seems to be working better and better, especially with the Coq platform. And I think when I last tried to install a new version of Coq on Windows last year, there were still some secret steps that you needed to know to get it working properly, and I just checked the installation instruction, and it seems that at least one of them has now been made explicit and even automated, so thanks.
Pass that to
the Coq platform is a bit of a worry in a way, and this is why we insisted to Romain that he should put some hand on it. Until now, it was a one-man project, and it's a one-man project is a bit of a risk, and especially the person who's doing that is also a senior person in his own organization. He has other topics to do, and so if anybody wants to get involved into it, I think we will try to make an effort with Roma to make sure that as much as possible is documented, to make it become more of a collective effort. Everybody can say, oh, I have this problem, but I found a way to solve it, and so that we share it more often. You know, the Coq platform should be collaborative, but not centered on the same developers that are doing the core, and it should be more of a community effort. So we are going to try to make it happen by making as much as possible documented on how to evolve the Coq platform. And well, I'm talking for Michael now, but I think he would agree with this. This is also the reason why we wanted to have an editorial board and things like that. That is to share more of the burden of taking decisions and finding solutions to bugs. Instead of having a single person doing it.
Thank you. So let me change the topic again. On the slides, you had something about better support for domain-specific logics like Iris. So what is the plan there?
Well, the idea is Actually, it links back to notations and scopes. Is to have the meta languages be more flexible in the way you can program the elaborator or the tactics, things like this. And also, in general, we are looking for, to fine-tune performance-wise the application of the iris tactics, for example, or tactics that work in a logic embedded in Coq. Yeah. So we're always interested in this kind of examples.
I see. One of the things about iris proof mode, the iris context is deeply embedded and it causes for very large proof terms, which slow down the QED time. Is there anything that you can do there to help? Is there any thought about that?
You could do it more effectively, probably. But I don't have a bulletproof answer.
Yeah, thank you.
To do it more efficiently, the iris tactics.
On QEDs, I have a pragmatic solution that's a no good, very bad hack that I highly recommend, which is to replace QED with admitted during CI. And occasionally run proofs. I would love to actually see this better supported by Coq. This is still a feature request that I would love to just skip proofs temporarily. I think for the most part, you don't need them when rechecking a proof. You only need to run proofs. You only need to check proofs occasionally for soundness.
But you want to check the tactics?
Yeah, I still want to run all the tactics. Those break all the time.
There is actually this experimental compiler is called FCC that can do that if you are interested. But yeah, it's experimental.
Regarding this question with the embedded proof context, so we thought about this really hard and we found no way to avoid, there's just some fundamental complexity issues here where things that should be O1 are ON, and then of course things that should be ON become ON squared. It's just like if you do I assumption, in Coq assumption X is O1 because you just refer to the name, but in Iris this has to go into the context and look up the nth assumption and check that it's what you want. And we tried to think about how we could avoid the strings, because strings are weird, to get shallow embedding stuff there, but nothing that we could think of was able to get rid of just this fundamental complexity issue. So, maybe we just didn't have the right idea yet, but I think there is some fairly deep problem there, maybe.
It's not just a representation of strings being...
No, it's not. No. We tried representing strings with like a 256 byte constructor per character, and that makes basically no difference. It's not, the strings are not the problem.
Okay, interesting.
That's great. That means we have some work to do as researchers.
Yeah, there might be actually research questions. Happy to talk more if you want.
This is really what we meant by, we think the iris is a bit of a front runner there, and we want to be able to be the system of choice to receive, to host this kind of domain-specific approaches to certain kind of logical problems. And so if we want to do that in a very principled way, there is a lot of work to be done, and I think that's among the roadmap ideas for the future ROC. Exactly. So we think you did a few experiments that show places where the sports really hurts, and so we would like to make this more fluid.
Yes, now that we are discussing that, just to mention, this thing you said about reflection, it's not really possible because it's the type class at search actually picking the right lemma, the right thing to apply. So we cannot really do it by reflection. So but maybe there is something we can do there, like, I don't know, with Coq-LP or whatever, to pick the right things. But within the way we are doing it, with the combination of type classes and tactics, and that's, yeah, I don't think we can do better than what we are doing right now. Yes.
questions?
More questions?
Yeah.
I guess following up on that topic, how many people have a real problem with proof term size and type checking at QED time? Okay. And I assume many of you use type classes to... So there's a big question about bundling and unbundling, and this obviously influences the standard library and math comp and things like that. Are there any thoughts on how evolution there might look?
Or what?
Or more efficient term representations or things like that. I know with type classes you end up repeating a lot of information a lot of times. I know Lean has things like memoized type checking and things like that.
We could try these optimizations as well. They've been tried before without so much success in Coq. Maybe we need to revisit why that was the case. Maybe just hash consting in OCaml is very different from hash consting in C++. Also makes a difference. There is ideas for research on trying to introduce a notion of arity, constants with arity in type theory, which would let you avoid repeating parameters of constants that we could, that we plan to look into to solve that problem in another way by just not repeating stuff that does not need to be repeated.
I'm speculating here, so there's a chance I'm making a fool of myself. But the part of my understanding for why memoizing type checking is hard in Coq is that type checking is like a global imperative step because of universes and things. And my understanding, which is very limited of Lean, is that somehow that's not the case. And I wonder if that's related to template universes. Like if you just don't have them, do you cease to have the global universe issues, or is there something that could be done to not have global universe issues?
I mean, the kernel type checker is purely functional. I don't think there is any effect there. So the universes are already taken care of separately. So if it's really the type checking of the proof term, then we should be able to memorize the purely functional structure. Yeah. I don't think the universes are, they're not a problem in this case, I think.
Regarding the complexity of type checking, I have a question about the cost of an application of a lemma. If I have a lemma that says P implies P, when I apply this lemma, how much does that cost me at type checking time, at QED time? I have the impression that the cost is linear in the size of P and not constant. So if I keep applying this trivial lemma to large subterms, then I will pay a lot at QED time.
So what's your example? You have P implies.
I have a trivial lemma with a small statement, but there is a for all P in it. And my impression is that if I apply it to a large term, then this is I'm going to pay several times for type checking P, possibly.
I don't believe so, but
okay.
Yeah, we need to look into the details. It's a standard type checking rule for applications. There's nothing. Yeah. Okay. So you need memorization to...
Yeah, maybe. Yeah, my impression is that I need memorization if I don't want my subterms to be retype checked many times.
Yes, in general, you would need memorization, which we don't have. Yes. Okay.
Thank you.
I'm really excited to see that you guys are thinking about bringing in ideas from observational type theory into Coq more. Can you talk a little bit more about what that might look like?
So right now, using the rewrite rules, there is a prototype implementation of this by Loïc Puget, Nicolas Tabarot, who have a version of observational type theory working with impredicative prop. And we are undecided yet if we try to actually do it directly in the kernel or if we stay at the using rewrite rules for now. I think the best exposition is their paper for what the theory is going to look like.
Thanks.
At Bedrock Systems, we've had some recent experiments with mechanisms for fine-tuning kernel reduction using the term language, and I think these are very valuable for computational reflective proofs. If you are interested in that, then I would be very interested in chatting with you. It's not really a question for you, but an announcement. Thank you.
I know Clément is interested in that too.
Maybe a bit naive question. I was a little bit away from the Coq things. What is the status of standard library std_lib? Is it an official way to, what should I recommend to the new novices? Just rely on the core library which comes with Coq, or std_lib is now the way to go? The recommendation?
I was finishing my notes on the previous question, so I will need you to repeat.
Is std_lib is now the recommended standard library for Coq? What is status of
what is status of std_lib?
What is status of std_lib?
I wouldn't go as far as saying it's now the recommended one, but we want to find a way to do a good synthesis with what exists, and std_lib is a really interesting proposal. And we really are thinking of doing more work on converging with this.
Any other questions or comments?
We have about 5 minutes, so maybe time for one more question, or we can go to lunch now.
Bas.
Hungry. We're hungry. Do you know?
I'll keep it short. What's the status of SMT integration in Coq? SMT.
Part of the work that's done with Tract and Troc is about making it easier to do all the translations you would want to have to use more easily SMT solvers. So the work is still active. But this is not this specific piece of work is not taken on directly by the very inner circle of the Coq developers. So something is happening. It's happening in a close vicinity because Chantal Keller is a close collaborator, but I can't really say that we have a roadmap for this.
And there are no projects actually actively using it? There are no projects actively using SMT?
No, not that I know of, but maybe my perception is a bit flawed.
Well, at least in the area of integration with Coq-LSP, we have the same plan as Isabel. So our goal is to do exactly what Isabel does. But yeah, I don't see that happening because, I mean, like, just no manpower now. So at least I think this will be a good start for Coq to do what Isabel people have done so far, I think. But yeah, but I'm not sure there is a lot of movement so far. Yeah.
Thanks.
Anyone else with a final comment?
Sorry, yeah, Gabriel took notes and he's going to put them on the Coq-LSP.
So you should have told me that before, because I was painfully taking notes on my phone. This is the example of collaborative work that we are doing in this community, you see.
All right, let's give our speakers a hand. And let's all head to lunch.
One small comment, lunch will be served in the Riverside room on the 3rd floor.
1, 2, 3. 1, 2, 3. Sounds good. Thank you.
Okay, everybody, welcome back. So we have 4 talks in this session. Xavier is giving the first talk, so let's give him a round of applause.
Thank you, thank you. I'm very happy to get an opportunity to speak in this huge room. So today I'm going to present a programming Perl, which means that it's a really trivial result that I feel that I like so much that I want to tell you about it. And it's about well-funded recursion. So where am I coming from? So you know, I develop, I write software in Coq and then prove it correct, and did that for a compiler called CompCert. And one thing I learned is that proving a program written in Coq is not enough to convince everyone. The program part of the Coq development, the data types, the function definitions, must still be independently reviewable by someone who does not understand the proofs or the specs or does not want to. Okay, the program should still make sense. And so this leads to 4 requirements that I try to apply to my own Coq programming. One is legibility. The function definitions should be easy to read for a competent functional programmer, should make it obvious which algorithm is being used. Then there's provability, so it should be easy to prove properties of the function separately from its definition. I mean, dependent types and so on are very nice and good, but sometimes you don't want to use them, and so it should be possible to prove things a posteriori, after the definition. No axioms. As we'll see, sometimes we are tempted to use axioms, like function extensionality, which I find pretty innocuous, but they raise alarms during review, so you have to explain why you're using them and why they are harmless. And then there, of course, extraction. So the extracted OCaml code should contain, well, no obj.magic, no extraneous computations. It should be clean enough to be debugged, for instance, if needed. Sometimes you've only proved partial correctness, and your program rises or stops on an error, and you have to debug that. And for most programs written in Coq, those 4 requirements hold very naturally. Take, for instance, a recursive function like this Euclidean division and modulus, which is structurally recursive on the first argument A. Well, it reads like OCaml code, so it's legible. Provability is easy. You just do an induction over A and some simplification, and then you're on your own. There's obviously no axioms needed. And extraction will produce idiomatic OCaml code, as much as piano natural numbers are idiomatic natural code, OCaml code. But today, I'd like to speak about well-funded recursive functions. So here, recursive calls are made on arguments that are strictly less than the recursive argument, but not necessarily a structural subterm, where strictly less than is a well-funded ordering. So continuing with Euclid, so this is the greatest common denominator computation, and as you see, the recursion is an A mod B, which is strictly less than B, but not a subterm of B, so it's not structural. And well, there are plenty of ways to define well-funded recursive functions like this in Coq, like fix, a combinator from the standard library, various Coq extensions, function, program fixed point, equations, or good old proof mode plus tactics, but I find them all, most of them deficient with respect to my criteria. For example, let me say a few bad things about the standard library combinator fix. So this is GCD rec written with fix. So as you see, it's a combinator, so it's a little bit hard to use. You have to swap the 2 arguments because the recursive argument B must come first. And then, well, there's this recursor, which, well, you can make sense out of the type, and then there's some proof obligation inside. So legibility is not great, but that could be tolerated. The one thing that I don't like is reasoning about it. So the first thing you need to do is to prove an unrolling equation, for which the standard library gives you a lemma, fix EQ, which unfortunately doesn't work well with curried functions of 2 or more arguments, because it requires an extensionality hypothesis. So basically it asks you to prove that 2 functions are equal. and I don't know any way of doing that in Coq except assuming functional extensionality. So provability is not that great, and it fails the no-axiom criterion. However, extraction produces excellent OCaml code. So the fixed point combinator is gone, and this is what you would have written by hand. So to summarize, with fix, so legibility so-so, provability so-so, axioms are often involved, and extraction is excellent. And well, you can see the other solutions I looked at. So program, for instance, is not good for provability a posteriori. And extraction is not great. Equation is almost perfect except the extracted code. Function is actually perfect on all 4 counts, but it's documented as legacy functionality to be replaced by equation. And what do I mean about the quality of the extracted code? Well, at the top, this is function. It's perfect. This program fixed point, some extraneous computations in there, extra pairing in particular. And this is equations, so it's getting worse with time. So I'm sorry, Matthew, I know you can do better than that. Okay, and I'm going to offer you yet another way of doing well-funded recursion, which is to go back to the basics. So, as you all know what a well-funded relation is. It's a relation where every element of the type is accessible according to this inductive predicate ACK, which means that all descending chains starting in X are finite. And it's a constructive way of saying that there are no infinite descending chains, and it's an inductive way to say it. And it's so nice so inductive that actually to do proofs by well-funded induction, you do proof by structural induction over a proof of accessibility. And that gives you exactly the induction hypothesis you wanted. And the trivial remark I want to do today is this also works for recursive function definitions. So let's see what it does. So going back to GCD, you start with a definition that doesn't work because it's not structural, okay? And then you add an extra argument, ACK, which is a proof of accessibility for the argument that decreases, okay? And you make the function structural over this proof of accessibility. So of course you get a little bit of a proof obligation here, which we will fill later. And now you just have to call it with an initial accessibility proof, which you can get from the proof of well-foundedness of your order. No problem. And so what should we put in here, the yellow underscore here? So not any proof, well, it's a proof of that A mod B is accessible. And not any proof will do, especially not LTVF A mod B, because it must be a subterm of ACK, the original accessibility proof, and it must be transparent. The fact must be obvious to the proof checker. And so I found that an easy way to satisfy those constraints is to use the ACK-inv lemma from the Coq standard library. It's just the inversion principle for ACK. So given the fact that X is accessible and Y is strictly less than X, it gives you that Y is accessible. It's transparently defined, and is guaranteed to return a subterm of ACK. And here, you just need a proof that A mod B is strictly less than B, but this can be any proof, opaque, done with tactics, whatever. And so, well, you can use program, for instance, to fill this hole, or refine, or just an explicit proof term, like this GCD obligation here. And in the end, you get something that is also very easy to work with when you want to prove properties. Basically, well, it's kind of tempting to do an induction over this ACK accessibility predicate, but then you run into dependent induction issues. So just do another well-founded induction over the accessibility of B, okay, and then destruct this accessibility argument. There's only one constructor, okay, so it doesn't create a combinatorial explosion. And then you can simplify the function, and you get pretty much what the unrolling equation in the fixed-based solution would give you, okay? And now you can reason by case, whatever, and you have an induction hypothesis. So reasoning is very easy, and extraction produces optimal code just because it erases the parts in prop. So in the paper, there are a couple of extra examples. And there's one that I would like to to show you, just to finish. So in the paper there's the example of Tarski iteration to find a fixed point of a monotonically increasing operator, and that's again an induction of accessibility of the current point in the iteration. So Tarski iteration is in red here. Okay, you start with bottom, and then you apply F repeatedly until you hit a fixed point, and it's the ascending chain condition, the fact that your order is well founded, that guarantees that it exists. However, well, people who do static analysis and abstract interpretation use that a lot, but sometimes their domain actually is not well founded, or sometimes it takes too long to find fixed point. Think of integer intervals, for instance. It can get bigger and bigger and bigger forever. So Patrick Couzeau and Radia Couzeau introduced widened iterations, which is the idea that, at every iteration you will jump a little up with the widening operator nabla. So the next point in the iteration is f of xn widened with xn, and the widening is a heuristic to accelerate the convergence. And so you may skip past the fixed point, but that's already pretty good. And the point I wanted to make is that so this relies on a non-standard ascending chain condition, which is here. So for every increasing sequence x, the sequence defined by applying widening at every step reaches a limit. There's a k, at which point it's, sorry, this should be y, at which points yk is yk plus 1, is yk plus 2, etc. And that's a post-fixed point you are looking for. And that can be reformulated constructively as an accessibility predicate of sorts. However, this one has two arguments, x and y, and it says that that for every increasing sequence starting in x and every widened sequence starting in y, you will eventually you will be stationary eventually. Okay, so it's almost like hack, but a bit more complicated. And now you need to prove that for every x, whack xx holds. And if you do that, then you can use that in a recursive function that will do the widening widened fixed point iteration, again, just by structural induction of a proof of accessibility. All right, so that's all there is to it, really. So wrapping up, that's a simple approach to programming well-founded recursive functions in Coq. Satisfies all my requirements: legibility, provability, no axioms, extraction. No extension to the Coq language is required. The calculus of inductive constructions is all you need. I think it's also more formative for students than just to tell them, oh, just use function or some other black box. It's an opportunity to tell them about accessibility and blah, blah, blah. As I showed, it extends to variants of well-founded recursion, such as iteration with widening. And of course, it's an instance of a much more general pattern, which probably underlies the function mechanism, which is recursion on an inductive description of the definition domain of a function. Thank you. I'd be happy to take questions. Plenty of time for questions. Yes? Ah, yeah, you need. The room is so big that you need a mic.
Thanks for the fantastic talk. I use this technique quite a lot, and it's very annoying that I have to redo it from scratch every time. So for every inductive type I have to redefine the right eliminators and everything, and it's very annoying. Is there a way to automate this method?
Oh, okay. You mean automating the so from a data type, automating the accessibility-like predicate that goes with it? Oh, it's an interesting question, actually. Nothing comes to my mind. Okay, I'm not saying it's impossible, but nothing comes to my mind. No, maybe some other people want to chime in. Question here. Oh, okay. Sorry.
I once published a paper on that was kind of formalization of widening operators as some kind of well-founded type. And one difficulty there was if you were trying to do some abstract domain, which was a composition of several simpler abstract domains, then you would have to compose the termination arguments, and then the proofs became extremely technical and complicated. Do you have any insight on that?
Not that much. So yeah, I had some experience with some simple domains for data flow analysis, and I know David Pichardy did bits and pieces of that in his PhD thesis too. Yeah, so the typical example that's difficult, if A is well-funded, then you want finite functions from B to A, finitely supported functions from B to A to be well-funded as well, and that's not trivial. So again, no, I don't have a general technique, but I think basically there's a few constructions that come that you have over and over again: lexicographic products, generalized products, sums. So it's a lot of bureaucracy, but it's doable. And I have no idea, however, how this would extend to this widened accessibility predicate. I guess a bunch of the theory of well-funded orders would need to be redone. And maybe it would not work as well. Ah, Mathieu at the near the right entrance.
I can do better, but maybe you can do better too, because
okay.
What you see in the encoding is just currying and uncurrying. When I have multiple argument functions, couldn't OCaml tell me that
it's not my natural programming style, and I think everywhere else in Coq functions are curried. Okay.
Yeah.
So, but yes, in a pinch. And if you curry now, you need an ordering over pairs of natural numbers, which ignores the first component. So you need a non-standard ordering as well.
Yeah, you use a measure. But I was actually, it's a real question. I expected that in OCaml, this curried function would be just as performant as the uncurried one. Is there a performance difference?
There may be. I mean, in some simple cases, OCaml is capable of turning a function that takes a pair into a function that takes two arguments. Here, it's a little more complicated because you have this extra function and whatever. So yeah, I would have to look at the generated code to answer.
Okay,
but yeah, I still prefer this one because sometimes I will have to debug it or run it under debugger, you know. So this one is so much nicer.
And then maybe to answer the first question, you can always derive the subterm relation of an inductive and prove that that is well-founded, and that gives you accessibility.
Okay, so that's a reply to
the equations as a derived subterm.
Okay, and that can be done automatically.
Yeah.
Okay, good.
It's actually the justification of structural recursion that that you can use to say that you could reduce any guarded fixed point to one that is just structural on accessibility.
All right.
Order.
Okay. One question here. Yeah. Question there. Question here. Let's do a random walk through the room.
Thank you. So this reminds me of large G Wendling and Monin's Braga method. So did you?
Yeah, well, we started exchanging email after I submitted the last version, the latest version of the paper. So yeah, definitely have to look at what they've been doing with their Braga method and the like. There are certainly connections. I have the impression this, I mean, accessibility proofs and so on is a very nice special case. And but yeah, another of my extended examples is with graphs and DAGs, and I think they have plenty of good techniques to deal with DAGs, some of which I don't know. So I really have to look more into what they've been doing.
Yeah, and I think there is, I mean, I worked also on trying to automate it, like connecting it with the general recursion monad from Conor McBride.
Yes.
So I think it's also not a possible answer for the first question. But
okay,
I mean,
good. Yes, yes. Well, no, it's your. It's theirs.
So there's one assumption you're making here, which is that if you write in the OCaml subset of Coq, then the OCaml code that you will get will be in the OCaml subset of OCaml. That is no obj.magic and the like. Is that a desiderata you have for the future of Coq? Because my understanding is that in the way to generating verified OCaml code, the plan is not necessarily to maintain that invariant. That readability of OCaml code is not necessarily considered a priority.
Well,
is that one for you?
Yeah, we see what happens. Yeah, the extraction facility based on the Metacoq project, for instance, targets an untyped intermediate language of OCaml and not source OCaml. So maybe I'll have to re-evaluate my priorities. I still think it's nice to have a readable and typable camel code. It gives a little more confidence in what we are running in the end.
And debugging.
And debugging, yeah. But well, it's a best effort, okay.
All right, let's give Xavier a hand.
Thank you.
Okay, next, Philippe is going to tell us about yet another approach to binders and syntax.
Yes, thank you, Tej. And I know this is an exciting talk about yet another, new way to build a mousetrap. But yeah, it's a talk about a sort of a new library based on at least a quarter-century old ideas. And yes, obviously, for a lot of us, we may think that syntax is a solved problem, solved issue. It took us a while. If you look at the early approaches to syntax of logic and programming languages, 120 years ago, it was a bit of a mess. It's got better, certainly. And obviously, okay, so a solved problem, right? So it's easy, just use, and depending on who you ask, you can get a host of different ideas, right? Just use HOAS, high order abstract syntax, or just use autosubs, so fancy the Brown index-based approach to syntax, or just use nominal techniques, just use locally nameless, just use, fancy universes of syntax. And the list goes on. So I will attempt to add to this list yet another approach based on functorial interpretations of syntax with binding. And there is a very sensible question whether we really do need more. I would argue that, yes, we can, in fact, learn at least learn something from the idea that there may be, other not fully explored approaches to syntax. And yeah, as you can see, the proliferation of standards reminds us, I think, of the proliferation of approaches to syntax. Now, as I said, this is work based on pretty old approach, and we need to go way back to the last century, back to 1999, as it turns out, where two papers were published. On one side, Marcello Fiore with Gordon Plotkin and Turi published a paper on whose theory, I suppose, this library is based. And this is a paper on abstract syntax, where the syntax is represented as special kinds of functors with appropriate monadic actions. And I won't go into too much detail about, the background mathematics of all that. This is the basis for general theory. On the other side, in JFP, Richard Bird and Patterson published a different paper that turns out to be very closely related. And it's a paper about a relatively simple observation that in Haskell, in 99 Haskell, you could use nested types in order to mimic the Brown indices, right? So the Brown indices, as we know them, of course, are not necessarily representable in Haskell, or at least you'd have to jump through, well, they are now, but they weren't in 1999. This is before GADTs were first introduced and all that line of work. So, and even today, you'd have to jump through SAM hoops, right? So the idea there is, well, you could index your type with the type of variables, right? And the representation They say basically, you know, with what Haskell gives us, we can write certain functions on these types. We need quite a sophisticated type system in order to write all the functions that are interesting, in particular substitution and appropriate folds over these sorts of types. But of course, if we're talking about Coq, we have a system that's at least as strong as we need it, right? Probably even stronger. So the idea is that we can sort of join the two approaches in this middle ground of interactive theorem proving or dependent type theory. And from Bird and Patterson, we can take the representation, basically adopting their representation or something that will at least look very similar. And because they don't really do any of the proofs or any of the theory, we can look to the more mathematical side and this whole notion of presheaves or special functors with appropriate actions and how they work as the representation of syntax and how they provide us with the theory of syntax for the theoretical underpinnings, for the proofs, for all the nice things. So how does it look, really? Well, the representation looks like this in Coq. We can take an inductive type of lambda terms over some set of variables. I think it may be a little bit better visible here, right? So we parameterize our type of terms with a set of variables. And then a variable is simply drawn from that set, and an application behaves like an application does. The set of free variables on both sides is the same. Now, the interesting bit happens in the lambda abstraction, as usual. And the point is, if we want to have a lambda term over a set of variable x, well, we need one more variable in the body, like we do with the Brown representation or any other similar representation, right? So in this case, we use a special type constructor, which is basically maybe, right? In order to say, well, I have one extra free variable in the body, and this variable is bound by the constructor. So this is the representation of Bird and Patterson. Of course, the set would not be there because it's Haskell, but other than that, this is basically the same constructor. And then the point is, in order to build a representation of syntax over this, we need to prove or show that the TM, the type of terms, is functorial in its parameter. So if we take two sets and a function between them, we can map that function over the entire type of terms. And we need to build an appropriate monadic action that will model parallel substitution. So this needs to be done in one step after the other. And this is, again, related to some of the ideas that came from early approaches to sort of proof engineering in the lambda calculus or in dependent type theory, also in the 90s. And so, okay, so this is all well and good, but where's the library, right? We can just, you know, take our type of terms, do whatever definition thing we need, and it's there, right? Well, a question that we could ask ourselves is, this is nice, this is, you know, a well-scoped representation. Can you make it well-typed intrinsically, right? And it turns out that you can, if you change the types appropriately, right? So this is a much more complicated definition, mostly because it's a type of terms that carries much more information with it. So instead of parameterizing it with a simple set, we're parameterizing it, our type of terms, with a context that carries some domain and types associated with the variables in that domain. And we're not producing a set, we're actually producing an indexed type that's indexed by the type of our term. And you can see it clearly in the variable case where we say, if I have an element of the domain of our context, I get a term over gamma of type gamma of x, right? And then the lambda and application case follow the usual typing rules. In the application case, I now have to take one type that's, one term that has an arrow type and another term that has the appropriate argument type, and I get a term of the return type, and vice versa in the lambda case with an appropriate extension of the context. And in essence, what happens here is we have the same pattern. We can ensure functoriality in the same way as we would in this sort of well-scoped case. We can give similar monadic action. There's some tricks required that I will sort of sweep under a rug. Do ask me if you want to know. And the idea is, now if we have a library, we can use the same derived theorems, same tactics, same support for definitions that are both well-scoped and well-typed, it turns out. Well, question is, how can we do that? And the idea is that we can build or at least our idea is that we can build a hierarchy of type classes. So basically the underlying theories from the 90s, the support that we have in Coq for making it go nicely, not just building a chain of definitions, but actually be able to use them nicely. It does require some support that came in later than that. And the idea is that we can start by specifying these indexing categories, which relate to either sets or contexts or possibly other things over which we will parameterize our types. Right? And these have to have appropriate structure. They have to be categories because that's how, well, basically because what we're realizing here is that idea of POPL'24 of building syntax as functors. Now, functors go from some source category to some target category, and in this case, they all will go into the category of types because we're building inductive definitions of syntax. So, we have indexing categories for base, layer, and for substitutions, and these are part of the library. And then, the idea is the user will define the type, like we saw in these two examples, plus the appropriate functorial and monadic actions, and they'll need to prove some properties to show that these actually have the right shape. What the library does is it provides additional supplementary classes which encode things like single variable weakening, substitution, the things that you actually want to use these definitions with going forward, and derived properties, tactics, all the nice things we can now define once and for all. Now, the idea is that because of the way that the thing is set up, particularly because these indexing categories are specified just as classes, and then we can provide different specializations of them, we gain quite a bit of modularity and extensibility in the library. So in particular, we have a lot of choice in terms of indexing categories. So the one that we usually use is the category of sets and functions, which gives us a very nice well-scoped representations, like the first one we saw. But because we're in a richer language than just Haskell, right, and because we could specify what we require from these indexing categories, we can also define an instantiation of the same library with contexts and context homomorphisms, which ensure that whatever we do with the domains of the contexts, the types match up as we modify them. And over the course of several years, we've used both these and other constructions. In particular, you can also build constructions on these. So we can have products of categories if we need to index our terms with two sorts of variables, that sorts of things. We're working on other representations. In particular, it's nice to have a nice representation of finite sets with functions for when we actually care that the support of our terms is finite. That is not usually needed, but sometimes it's nice to know that. And obviously, you can roll your own. So one of these nice consequences of this choice is that if you want, for instance, to have linear notion of syntax, you can replace the category of sets and functions, where you can weaken or contract as you want, with a category of sets and bijections. And the point is, because of the way that the hierarchy of type classes is set up, some of the things that you would get for sort of normal intuitionistic syntax, in particular single variable weakening and single variable substitution, which don't really make sense in a linear setting, will not be available to you, because you wouldn't be able to construct certain instances of type classes in this setting. But all the basic ones will be available. Another nice thing that we gain from this is an interaction between indexing categories. So for instance, you can have interaction between well-typed and well-scoped categories. Your syntax may be well-scoped, but it may interact with some typing information as well. And it allows us for flexible binding and substitution structures. In particular, we've used this for, I think, some lambda mu related formalizations where the context variables behave in a slightly non-standard way. And yeah, of course, it's got a lot of limitations as it is, because at some point you run into the usual problem with formalizations, where certain things become expressible, but very difficult to use in practice. And in my case, this was when I tried to see whether I can build a well-typed church-style system F representation, where you can only represent the completely well-typed system F terms, so polymorphic lambda calculus terms, which is possible, but basically the syntax becomes very difficult to use because of the complexity of the indexing category. So the other interesting consequence is the fact that the very definition of syntax as a functor gives us some useful notions. And one of these that we've noticed recently is that we can actually build certain constructions on functors, including in particular function space, which is sort of limited to well-behaved functions of certain shape. And this allows us to build things like normalization by evaluation algorithm within Coq. This has been done before, not necessarily in Coq, but certainly in Agda. A nice twist that we've recovered using this syntax, and precisely as a consequence of functoriality, is that we can get precisely the sort of interpretation that is necessary. So there is no need, you don't get too many functions in the function space, and so you don't need to reason post hoc. You get precisely the sort of representation of normalization by evaluation that you need. And there's possible other applications. So for instance, in translations to continuation passing style, there is usually some sort of need for interplay, safe interplay between continuations and scoping, and the idea is that hopefully functoriality of the continuations would allow you to safely plug it into a larger scope. So this is the rough idea of what we have, and there is definitely need for more automation, and because right now the system is rather heavy on boilerplate. So I can show you a simple definition here. So this is a definition of a variant of system T with values and expressions. And so this definition is precisely of the shape that we've seen on the slides. But of course, it's not enough to just give the definition like that, we need to then define all of our functorial actions and the monadic actions, the substitutions, and prove quite a bit of boilerplate. There is some automation support, so there are tactics for this that will take care of your proofs in most common cases, but you still need to make quite a few definitions like that. So I think I'm slowly running out of time. So if there's any questions, I'll be happy to answer. And if you'd like to know more, please talk to me.
Thanks. This looks like really interesting work. Have you looked at all at syntaxes with multiple types of variables that may need to interact, or?
Yeah, so in general, this sort of arose from whatever we were formalizing, Piotrek and I were formalizing in the last 5 years or so. And we have had a formalization where we needed 2 different sorts of variables. This is possible. You get a little less for free than you would in a single variable case, because I think in a lot of cases it's very easy to figure out what the functorial action should be just based on the shape of the type. But with the substitution, it can be a little bit more tricky. There can be some interaction. So you may need to do a little bit more legwork in terms of showing that your substitution behaves as it should, but it's actually, completely usable with the rest of the library. Once you're done with these definitions, the rest of the support, simplification support, and proofs, derived proofs generally work reasonably well.
All right, I think we're running out of time, so let's give a round of applause. And
thank you very much.
Okay, so next up we actually have 2 related talks. So Lassi is going to give the first talk, and then we're going to switch over to Boss for 2 related papers where one builds on the other.
Thank you. Yes, so I'll start by introducing what I've been working on here. So we'll start by talking about why we are looking at smart contracts and why we actually want to formalize smart contracts. So first, what is a smart contract? So a smart contract is a computer program or a transaction protocol that is intended to automatically execute, control, or document events and actions according to terms for a contract or an agreement. And the primary idea is that we can actually specify and execute things in a very precise manner. However, sometimes these implementations of smart contracts actually go wrong. So we would actually want to specify these or formalize them. And furthermore, we can see that there's actually getting a more push for doing these formalizations. So the Data Act for Smart Contracts says in one of its subsections about robustness and access control that you need to ensure that smart contracts avoid functional errors and withstand manipulation by third parties. So what this actually usually looks like is that you're doing a lot of testing of the smart contracts to ensure that they're not doing anything wrong and you're just doing validation by inspection. However, as we're getting better tooling, we think that you should use formalization for actually doing these things, and we'll show how we do this. So first, a bit about the landscape. So smart contract languages have developed over a long period of time. So they started out with the Bitcoin language, which called Script, which was not a fully Turing complete language, but just done for simple scripting. And then we got a more expressive and more modern blockchain like Ethereum, which uses Solidity, but Solidity is not the best thing to code in. So more blockchains have developed, and more layers on top of Solidity has also been, or on top of Ethereum has also been made. So, for example, we now have examples of smart contracts using Rust and WebAssembly to actually run. So, for example, the Concordium blockchain is using Rust as a smart contract language, and Ethereum using rollups is also using Concordium, or also using Rust with WebAssembly as backend. And others are like Polkadot, ICP, Cosmos, Nia, Hyperledge Sawtooth. So there are many examples actually using this. And the different goals of many of these are also a reason that there's so many different blockchains. So here, some goals could be performance, developer experience, how the quality of the blockchain, and interruptibility between different blockchains. So some build that on actually being able to interact with different blockchains. And we even have languages, functional languages for some blockchains. So like Plutus, Icon, and Cardano are a functional language for Cardano, and Cameligo is a functional language for Tezos. Yes. So we want to say that given this landscape, we can actually do the specification and implementation of smart contracts in the HEX framework. So the HEX framework is provides a language which aims to be a middle point for a lot of people. So it aims to target cryptographers, proof engineers, and software developers. But it also has these backends to Coq, EasyCrypt, and FStar, and more backends are being added. It tries to make internet standards machine readable, and it's a simple subset of Rust. However, you might say, why would we want to use HEX if it's targeting cryptographic specification? However, here we want to say that specifying smart contracts actually aligns very well with this space, as we also want machine readable specifications that you can test against. This being a subset of Rust is also a very nice feature, as many smart contract languages are using Rust. And we also want to have a community where we can collaborate between people actually implementing the code and having some formal validation of the specifications. Yes. So if we want to look at an example now. So if we're given some smart contract in Rust, what we would want to first do is take this smart contract written on the side here, which takes a context and a state, and then it returns some actions for the contract. So what we then do for translating into HEXspec is that, or into HEX, is to do message state passing instead of just having the mutable state. As HEXspec is a functional or semi-functional language, so we don't have a mutable state in the language. So you would have to refine your contract to actually fit inside the subset to do the first step of this specification. This allows us to actually do proofs about functional correctness. However, we don't just want functional correctness for our smart contracts, we also want cryptographic security, as many of these smart contracts build on cryptographic primitives, so many use zero-knowledge proofs and things like that. So we would want to get also cryptographic security of our implementation. And one way we're actually doing this is using the SSProof framework. So SSProof is a foundational framework for doing modular cryptographic proofs inside of Coq. It takes and embeds a probabilistic stateful language inside of Coq, and it uses the Dijkstra-Monad framework to give us a way to reason about these programs. So you can actually take the code generated by HEX and reason about the cryptographic security of that inside Coq. So this is also now a backend of HEX. This was work presented at CPP, adding this backend to HEX. And this allows us, as I said, to do better security proofs of these contracts. However, we are only doing security proofs for like individual functions and not more broadly the state of the smart contracts. So how does this translation actually look? So we are translating into the equations definitions, and the reason we're doing this is because a lot of the translation is using proof obligations. So we are solving all of these proof obligations about how things move around in the flow of the original program. Specifically, we can look at things like proving the validity of the programs of SS proof can be solved automatically using these equations. As the hex language is very simple and structured, so it's easier to do a lot of automation on actually validating the code. And this also allows us, as I said, to show security properties about individual functions. Now for going beyond just individual functions and looking at more general interactions, so a contract usually uses a lot of state. So if we want to look at how the state changes over time and ensuring that we are not doing anything wrong, entering in a bad state or anything like that, we are using Concert. So Concert is a smart contract certification framework in Coq. It facilitates property-based testing of smart contracts using the QuickCheck library, and it has extractions to Rust and Elm and so on. What we are using it for here is taking the SS proof code and actually doing testing on that. Yes. So we can now look at why we are doing this embedding into to Concert instead of taking and just extracting from Concert, as it has extractions directly to Rust. So you could just specify a smart contracts inside of Concert and then extract to Rust instead. So what we want to say is that embedding actually gives us better looking code. So if you just take the extracted code from Concert, it produces a non-idiomatic Rust code. So for developers actually working with this, it's hard to continue working or building upon code generated. Furthermore, the embedding also allows us to annotate the code and add features from the hex toolchain on top of just the smart contract code itself. So by annotating the hex code, we can automatically translate some of these annotations about the message passing and the initialization of the smart contract into Concert, and inside of Concert we can then wrap this behavior inside a contract type, which allows us to just look at the behavior of the contract isolated in Concert. So we can actually do some proofs of traces of behavior, and we can do property-based testing of these things. And furthermore, we connect these annotations up to existing libraries. So so what we're doing to achieve some of these things, to actually meet developers where they are, is that we take smart contracts and embed them inside of Rust instead of extracting from Concert, as this gives us better looking code. We take annotated properties for tools. So we take and annotate properties inside of hex to get extractions to tools and extractions with tools. This can look like a QuickCheck where we have specified inside of hex the QuickCheck properties, and you can test them directly in the Rust code layer, but you can also translate this to Coq and do a QuickCheck testing inside of Coq and validate that you're actually getting the same results as you were doing for the testing on the original layer. So we have this multi-layer tooling connection where we both have the tooling on the Rust layer, but also on the Coq layer. And this also extends to tooling for Creusot or PLite language, where we have specified annotations inside hexspec or inside hex, which is then taking the subset of PLite that fits in within the subset of hex and translating that to Coq. And then we can take the proof obligation generated there and actually validate that the proof obligations are doing the correct thing, like validating proofs, where Creusot just checks them in Y3. And lastly, we can use the entire concert framework to actually reason about and encapsulate the behavior of smart contracts as a whole. Thank you. Questions?
I have a question. So, how much of this do you think developers, how much of the specification do you think developers have in their head versus would need help figuring out? I mean, do developers have a more abstract perspective on their contract?
So I think developers know a lot about what guarantees they expect from the contract, but they will probably require a bit of like getting used to a training for actually just taking the abstract model they have and actually writing it down in code and specifying it. But I think this is a good step towards getting used to that, because you actually put the specification in the hands of the developers and not just having it as you have to have proof knowledge in Coq to actually be able to do these things. And it also allows you to do like automation, as a lot of these annotations for the developers and getting some of these properties written down allows you to see what the class of problems you actually want to automate and the class of problems that are very general for these smart contracts. Yeah.
Any more questions? And just one more question. So do you have examples of, like, what examples have you done so far?
Yeah, so...
And what do the proofs look like?
So we have a couple of very simple examples, and then we have the next talk as a good example also. So examples basically look like a 1 or 2 lines of annotating properties on the smart contracts. And the extracted code it's readable, it's close to the surface level code, but there is a bit of extra annotations to actually translate these things. We have actually been able to show security properties using this framework to translate. So for other protocols, not smart contracts, we have done the entire translation and shown realistic security properties for something like AES. So you could expect, like, if you have smart contracts with AES as a sub-protocol, you could actually extract and validate that using this framework. However, extending that, we can also look at the extracted code for the smart contracts itself and do proofs on that. However, we haven't done that for any examples yet, but we expect to get a library of examples soon.
Okay, then let's thank the speaker, and boss, you can get set up.
Is that the first slide? Yeah, thanks. So welcome. The talks are actually in anti-chronological order. So quite a bit of this work was done before we started to work on the embedding of Rust into Coq. But then we thought that there's actually the whole tool chain we have with Hex is actually probably a nicer way of doing it. So that's why there are 2 talks. So this is a bit about formal security analysis of a blockchain voting protocol, and this is a fairly small, or this is an election that works for smaller groups because you need to do everything on-chain. We're working with an industrial application of actually putting this in practice, and a protocol like this one will be used to hold elections on the Concordian blockchain. So there will actually be a lot of money involved. Because if you can rig the elections, then you can actually take over the foundation, so you can get quite a bit of influence. So this is also what Lester just had on his slide. So there's the new Data Protection Act. So it says we should have a very high degree of robustness to avoid functional errors and to withstand manipulation. The law never says precisely how we should get these guarantees, but by pushing the technology, we can actually influence the interpretation of the law. So if it's actually feasible to develop these things completely formally, then if you would carry this out, you have such a thing on chain, and it would break, then it's, I mean, the onus is on you to actually show that you actually did your work well. So that's one of the reasons why we're doing this. We want to show, well, this is currently possible with, well, fairly limited resources. I mean, there's a lot of money sailing on these contracts. So if we invest a moderate amount of that on security, then actually we can get something that has a very high level of security. And there's what you can see here at the bottom. There are more and more experiments with electronic voting, and there are many challenges with that. So they're common in Estonia, they're common in Brazil, they're common in India. There's new regulation in, I believe, Germany, where they're also experimenting with it, and then there are caps on saying that only, so often it's for mail-in elections. I think the current Swiss regulation says it can only be used up to 1/3 of the population. So there are more and more experiments with it, but it's people are still careful with it, and for very good reasons. And this is part of an Innovation Foundation project to actually make these voting protocols much more secure, and also really looking at electronic voting. So there's a tight connection between voting and blockchain. So we see voting in the screen here is very small. So we see voting used in blockchains. So actually the consensus already uses a voting mechanism. We have the governments, where you can see who gets to control the chain, or who gets to control a smart contract. We have these decentralized organizations, and most people will recall that on Ethereum there was a large amount of money on such a decentralized organization, and due to a re-entrancy bug, people could steal a lot of money from these projects. So already in this voting, we know that it's a very tricky situation, and it makes very good sense to use a bit of formal methods in this space. On the other hand, and that's the focus of the talk today, you can use blockchains. So any voting needs some kind of bulletin board to publish the results, and you want to publish the results in such a way that people can actually check by themselves, my vote has been counted in the right way. And that such a bulletin board could very well be a blockchain. So that's how we're using it here. And the nice thing about a blockchain is you cannot change it, and it will always be available. So there's a lot of duplication. So specifically, what we're looking here at is what are called boardroom votes. So you think in a lecture room like here, and that's sort of the size what one can do in these votes. So also lots of things about manipulation of who votes and so on, coercions, they're not so urgent as they would be for national elections. So the setting here is a bit different. So there's this open vote network, which has been launched on Ethereum. It has been running for a while, and people use it, and you can use it quite pleasantly for small elections. A bit about the setup. So you use a group that has a hard Diffie-Hellman problem. I think most people have seen this. And you have 2 rounds. In the first round, the public keys are put on the chain and they're verified, and then the reconstruction keys are computed. And these keys are computed off-chain. And in the second round, the ballots are computed using the reconstruction key, and we have a zero-knowledge proof that this ballot actually is a valid vote. So it's either 0 or 1. And then finally you put those on chain, and then anyone can check that their vote has been counted correctly, and anyone can check what was the result of the vote. So how many people voted in favor of Coq over Lean, say. So these are the formal properties. So self-tallying. So everyone can check that their ballot was counted correctly. Everyone can compute the results without any external help. We have maximal ballot secrecy. So each ballot can be, so we have this in CPA. So that's a well-known property in security. So it's indistinguishable from a random number. And then finally, the result is publicly verifiable. So anyone can check that the whole election was actually carried out in the right way. So now what do we want to prove about this smart contract, about the voting contract? So one is, so was it cryptographically secure? And the other one, was it implemented correctly? Already the paper about the open vote protocol, it contains an analysis why this protocol was secure. We checked it carefully, and it's almost complete, but there's some steps missing, and that often happens if you write a proof on paper. So there is a cryptographic proof, but there were some, we needed to work on a bit on it to have a complete proof. And then we want to verify that proof of that protocol. And then, of course, on top of that, so the paper about the Ethereum implementation, or even the first paper that was not connected to a blockchain, there was nothing about the implementation, or nothing proved about the implementation. So the first thing what one would want to do is prove things about solidity. As far as I know, there's, say, no Coq library that allows you to do substantial proofs about solidity, and I'm not aware of any other tools either. There's some more lightweight tools to check some things about solidity. But there's certainly no interactive framework. So the first thing we did was to re-implement this in Coq, and for this we used our Concert framework. So Concert, it models an abstract account-based blockchain. So there are 2 models of blockchains. One is using accounts, so that's what Ethereum is using. The other one is using UTXO, so you keep track of the unspent transactions. So that's Bitcoin and a number of others. But we stick to this particular model, and then we have pure smart contracts. And as Lasse mentioned, there are quite a few blockchains that are using pure smart contracts. So that's a good motivation that this can actually be done. And there's you can write many of the smart contracts you would like to write in that style. Of course, it's pure programs that manipulate state, because you're always interacting with the blockchain. So there's one big state that you're updating. What we're doing, and this is something that Mathieu also touched on in his presentation about what's going on in Coq. So Concert is part of this big ecosystem that we're building collaboratively, where we have the Metacoq, CertiCoq, verified extraction, and so on. So this is part of this. So we do extraction from Coq to Lambda box. So that's basically formalizing in Metacoq the extraction that was in the paper by in the thesis by Pierre. And then we have a small printing layer. I have a picture on the next slide. A small printing layer to Rust and to Lego. So Rust is what's used by Concordium, and then you want to do also a bit of glue code to actually connect to the blockchain, and the same for Lego. Another thing we've done was to add quick check testing, so you can test temporal properties, you can test functional properties, and what we did was to implement quite a few of these paradigmatic contracts like a DAO, decentralized exchange, an escrow, an ICO, and then we looked around at some of the big hacks, so everyone knows what was wrong with the DAO. There were the reentrancy issues. For the DEX, there were a number of attacks on these things, and basically what you do is you write down the property that if you exchange coins, then the total number of coins should stay the same. And what we did was use quick check to actually generate traces, and then you can actually find these attacks there. And so we could actually reconstruct these 0 days. So if you would actually have, well, while you were implementing them, write down the invariants, you would have prevented these attacks. So here's a picture of what this thing looks like. So this is now part of the whole verified extraction CertiCoq pipeline, the optimizations that we added there. And so what we can do here at the end is from a lambda box to a small printing layer. So a big part of this is actually verified in Coq. So what we did was to actually implement this open vote network in Coq, and then prove that it's correct. And that gives us the first property that we want. So OVN is actually self-telling. So that's just a functional property. And what I should mention, this is actually an industrial application of Coq. So this was supported by 2 different blockchains. So we both support the Concordium blockchain, which does Rust, and the Tezos blockchain, which does Lego. Now there are two more properties that we want to check. So there's this maximum ballot secrecy and the distribute freeness. Now just a refresh on how you do cryptographic proofs. So there's this provable cryptographic security. So you have a mathematical argument reducing. So if I can attack this protocol, then I can also break this really hard mathematical assumption. And that could be something like prime factorization, or here the Diffie-Hellman assumption. And this is called game hopping, because you're reducing one protocol to something similar. What we need there is a computational framework that captures probabilistic and stateful algorithms. So that's what we have in the SS proof system. That's together with Theo and Lasse and many others. So one observation, and that's something that people have started to appreciate, for example, in the Everest project, is that the game hopping usually is not very modular. It's been directly also observed by, in the book Joy of Cryptography, that actually writes a bachelor level textbook on cryptography, where they actually found the same style. What you do there is you take code blocks and you manipulate them quite nicely. And I think that this can probably be extended a bit further in programming logics. But this is something that cryptographers quite enjoy. Before SS proof, this didn't have a formal semantic. So what we did in SS proof was we took this picture calculus and we actually put it on top of a program logic. So this is a library in Coq for the state separating proofs, and it's based on the Dijkstra monads framework that was developed also to get the semantics for things like what one does in F-star. And we look at the monads for state and probability, and these can be combined in a modular way. Yeah, that's what I said. So the program logic is a probabilistic relational Hoare logic. And you've probably seen this in EasyCrypt Proof Assistant. So what do we prove? When did I start, by the way? Because okay, that's great. So what we do is we have there's this general notion of zero knowledge protocols called Sigma protocols. So that's the class of zero knowledge protocols that we're looking at. And then there's a number of constructions. So if you can prove certain properties in zero knowledge, you can combine them with what are called the AND and the OR construction. So you can prove two things that one of two things hold. And we did these constructions, both the basic properties of Sigma protocols that it is a zero knowledge proof, and also these OR and AND constructions. So the OR construction is what we need here. And then we also did the Fiat-Shamir transform. And this is typically something that's very hard to do correctly, and that's where there were some real world attacks also. So that's good that we're actually verifying these things. And so what we have in Concert is an actual model of the execution, the scheduler of the blockchain. What we have in SSProof is we also need to model the blockchain state in some way. And what we did here was to take an ideal functionality in the sense that cryptographers do it together with a scheduler. And then we prove in SSProof that the OVN has maximum ballot security and is dispute free. So those were the two properties that we still wanted to prove. And then, yeah, as I showed you before, what we can do here is actually extract to all these languages, to Cameligo and to Rust. That there's a bit of overhead in Rust because you're going from a functional language, Lambda box, to Rust. So you don't get idiomatic Rust code. It's also a bit slower than you would want, and especially if you're running on a blockchain, you want to be careful there. So there's an alternative that we can do, and that's what Lessa presented. So instead of extracting from Coq, we can embed code into Coq. And that's what we've been doing with this whole HEX framework, which is a framework that we're collaborating across provers. So it's also being used by people in F-star, in ProVerif, in EasyCrypt. So we have a joint language and a big joint pipeline. And what Les also pointed out is there's an automatic proof of that the imperative code actually refines the functional code that we generate. So we have, instead of what we first did by hand was we proved those two programs to be equivalent by hand. Now we just write the Rust code once, and we have this translation into the two libraries. I should also notice that both these libraries, they're very, very big. I mean, Concert uses both QuickCheck, it uses quite a lot of Metacoq, so it drags in a lot of dependencies. On the other hand, SSProof also, has a lot of dependencies. That's based on MathComp. So actually automatically proving that one refines the other, that there's quite a bit of infrastructure that goes into that. So to connect with the first presentation we had this morning, we're now going from either Coq to Rust or from Rust to Coq, but still we're trusting the Rust compiler. What would of course be nice, in the end what we have running on chain is WebAssembly. So if we can go efficiently directly from Coq to WebAssembly, that would be even better. So yeah, that's what I tried to show you. So we have the first smart contracts that was both proved functionally correct and cryptographically secure, and we have very general libraries that can be used to prove these things. And we're building a whole infrastructure using HEX and using these big libraries. And both of these can be done by either extracting or by embedding from HEX. Now, just want to pitch a project that we're actually working on. So there's a project by the Innovation Foundation. And what we're going to do is to collaborate with the Microsoft. So Microsoft has a team building the election guard. So election guard is actually used a lot in practice. So it's been used in the Republican primaries, for example. And it can not only be used in electronic elections, but also in physical elections. So this is a very real product. So what had been done before was that the crypto that was in there was replaced by Hackle, so that they actually have formally verified cryptographic code already in there. So that was version 1. What we now want to do is replace that by our libcrux library, which is a library we're developing together with Crispin, which actually brings all verified crypto together in one joint Rust library. And then what we've shown in this project is we can do these zero knowledge proofs that go into the OVN, and those should scale to election guard. Doing that is still a big project, but it's the direction we want to go in. But that's what I wanted to tell you. Thank you. It's been a long week.
So actually, I did have one question. So do you have a sense for, if you could only prioritize one, whether there are more bugs in the implementation or in these high-level protocols, thinking about security bugs?
We know that almost all the bugs are memory safety bugs. I think that's...
I mean in contracts, right? So
in contracts. I don't think we've seen enough.
Okay.
Well, chain analysis has very nice overview of attacks on smart contracts or attacks on blockchain projects in general. Also see how they're abused by criminals and by nation states and so on. They have a breakdown. So part is it the economic incentives, which is out of scope of this work. And in part that's a field of cryptography that's still being developed, so rational cryptography. There are quite a few that are functional correctness bugs that could be implementation of rational numbers, but also off by one errors. What I mentioned, something started moving here. The other one, the Fiat Shamir that I mentioned, that's come up here, that has been a real issue in zero knowledge implementations, and that's very acute because they had a bug in Zcash, for example, where there was basically an off by one error. There was a very nicely published paper, and they had used a different convention in the indices, and this was faithfully implemented by the software engineers. This would allow you to print as much money as you want, and it would be completely untraceable. So those bugs in cryptography, so this was a functional correctness bug, but the related Fiat Shamir is also something that's very dramatic. So in both, we have very real examples in both problems in functional correctness and in cryptographic security.
Thanks for the talk. You briefly mentioned the Coq to WASM certified compiler. How does that compare to the current setup with Concert, and would there be any drawbacks compared to your current setup if you were to change to that compiler?
Not a lot, I think, because yeah, what I show here. So basically, what we do here. So we optimize in the box, and then from there on we use the same pipeline. So this has now been integrated in verified extraction and in CertiCoq. I mean, that's the integrate part has been done meanwhile. So then we just continue this line and end up in WebAssembly here. What we don't have, I think, is what we should probably do is some kind of foreign function interface, which is something we've been discussing, because you need to do the interaction with. So now we have glue code to get the interaction with the blockchain, and we would need something similar at the WebAssembly level. But in general, I don't see an obstacle using that line of attack. Whether that's fast enough, I think that could be fast enough. That there's a big question of whether you want to have a garbage collector on chain. I've been talking to some of the engineers, and they said, well, even if people add a garbage collector to WebAssembly, we probably don't want to have it on chain because it's too unpredictable. But otherwise, I don't see obstacles, but it's also not something that we've pursued very actively. But I think it's a very interesting direction. Thanks.
Okay, let's thank Bas. And we have a half-hour break now.
Hello?
Okay, so I'll use the handheld one. Okay. Oh wait, now it's working. What? Okay. But now it's off again. Yes, hello? No. Wait, it really depends on the angle, I think. Now it's doing nothing? Or is it doing something? Okay. It's very specific.
Yeah, you can
Wait, let me just try and put it in a logical position. Hello? No, I don't think it's very reliable. Or is it? No? No? Maybe? Can you hear me all right? If I talk like this?
The problem is not you, the problem is the recording. Yeah. Yeah. It's because
Oh, it's recorded as well.
Yeah, yeah.
And this one isn't being tracked. Or?
Now it was because it was strong, but when it's not reverberating.
Yeah.
Seems
Okay.
like this is gonna do a better job.
Okay, I'll try the hand.
This is gonna do a better job. It's more reliable. Yeah.
Yes. If you turn it off.
Test 1, 2, 3. Okay. Oh, by the way, can you check if the connection works? Yes. Oh, hello. I'm Jacco. Yeah, we tested the other one, but it wasn't reliable. Yeah, that one's off too, I think. Yeah. Okay. I mean, I don't really mind, but I might start walking around and forget about that. Yeah.
You know how to use these mics?
Not really.
Okay, so
Constant distance. Yes. I will move with the microphone. Okay, can you please just signal to me if I forget or something?
The mic is not a magic stick that makes everybody hear what you say.
Yeah.
And in fact, it does worse than that. If you do this, then it is in fact super annoying.
Right. Okay.
Yeah, it's 4 p.m. So bring 90% of your maximum energy.
I forgot my background music, but okay.
All right, so thanks everyone for coming to this very last session of the very last workshop of this long conference marathon. First talk is going to be by Jaco, who is going to tell us how we can avoid writing LaTeX ourselves in the future, I hope.
Yes, thank you all for coming to this last session. I know it's been a long day, or maybe a long week. So this will be a bit more of a practical talk. Yeah, my name is Jaco. I'm a PhD student at Utrecht University. And yeah, I'm going to talk about this little project I started, which I call InductTech. And the problem I'm trying to solve here is that I write this little piece of Coq code with some inductive definitions. So in this case, it's the simply type lambda calculus with the syntax and the typing rules. And basically, I'm looking for a magic button I can press to give me the LaTeX inference rules. Yeah, so I looked around to see if this has been done, but I couldn't really find a good solution. So yeah, I decided to build something myself. But first, before I go into the how, I'll tell a little bit more about the why. So yeah, the main topic of my PhD research is this compiler, the Plutus compiler, which compiles a subset of Haskell into this lambda calculus. It's specifically system F omega mu, so it's a polymorphic lambda calculus with recursive types and type functions. But the Plutus compiler is a real compiler. It's implemented in Haskell. It's under constant development, and it's mainly used for compiling these smart contracts that we've heard about in the last session for the Cardano blockchain. So just a very brief, my version of the definition of a smart contract. It's a program that facilitates financial transactions between participants based on a predefined set of rules. And there's an obvious need for either formal or informal reasoning about the correctness of these smart contracts. As we've heard before, there have been numerous very costly bugs in this blockchain space. So what is interesting to think about is the deployment model of these smart contracts. So basically what happens is in this high-level language, in this case Haskell, the logic is written down, it's compiled down to this low-level lambda calculus, lots of optimizations happen, and this compiled version of the program is then sort of deployed as an entity in the blockchain, and participants who want to participate, they sort of have to trust that the logic of this obscure low-level program does what it's promising to do. So what we want to do in my project is to, given the source code or the supposed source code of that program, also a verifiable link or certificate that on the one hand relates the source code to the compiled code, and on the other hand shows that the compiler did not introduce any bugs in the process. So when you know you are looking at the actual source code, you can start doing this reasoning, and we've seen some interesting talks in the previous session on how you could do that. But this is more about enabling that kind of reasoning and making sure it's, well, trustworthy end-to-end in the compilation process. So the approach we're taking, we're calling it translation certification, and it's basically based on the well-known idea of translation validation. So what we're doing is we're treating the Plutus compiler in this case as a gray box system, and the compiler is in this case a multi-pass pipeline with optimizations, translation steps, etc. And yeah, what we do is when the compiler runs, we basically dump all these intermediate forms of the program, and then yeah, we build a system on top of this. So for each compiler pass that exists, we define a formal translation relation that sort of captures what each compiler pass should do. So this is like an inductive binary relation on ASTs. You could present it like a set of inference rules, and this will be relevant later on in the talk. But basically, it's yeah, a way of describing the specification of a compiler pass. And we do this completely independent from the compiler, because also in this case, the compiler is not implemented in a proof assistant. The Plutus compiler is implemented in Haskell, but we can write these specifications down in Coq in this case. And the nice thing is that, for example, here, this is the specification of an inlining pass for a simply typed lambda calculus, but it's typically a lot shorter than writing down the actual implementation of an inliner, which may rely on some magical heuristics, on deciding which terms to inline, etc. But this relation captures all possible valid ways of inlining terms in the program. Okay, yeah, so like I said, we define these binary relations in the Coq proof assistant. And then the next step is that we implement a decision procedure, so that given a preterm and a post-term, is what we call them, that are dumped by the compiler, we can decide whether they are indeed related through this specification. So then we have all the basic building blocks to build this translation certification infrastructure. And on top of that, we then prove that any related terms are also semantically equivalent for some definition of semantic equivalence. Now, so I briefly mentioned that we built this system on top of the actual compiler, and we call this system the certifier. So what it looks like if you have a run of the compiler here on the left, where on the top you start with the source code and you step-by-step translate to the low-level lambda calculus version. What we do is we dump the programs, and then we read them back into the Coq proof assistant so that we can formulate all the theorems, basically stating per pass that the specification is adhered to. Then we run all the decision procedures to actually produce all the proofs for those. And then we use the equivalence results to build one compact proof object, which basically states that the source code is equivalent semantically to the target code. Now, the point is that when a participant in the blockchain space want to sort of participate with this compiled version of the contract, they can now look at the source code together with this proof and basically push it through the Coq kernel and get the approval that this is indeed the compilation we were talking about. And the nice thing about this setup is that we have a small trusted computing base. Basically, it's the Coq kernel together with all the definitions that make up this theorem that's being proved by the certificate. Okay, so let's get back to this first step of specifying these translation relations. So again, here's an example. This is the inlining I was talking about. So the judgments here take the form, they look a bit like type judgments. So it says gamma, under gamma, an inliner can transform term T1 to T2. In this case, gamma is not an environment of type assignments to variables, but it's basically all the lab bindings that are in scope. So it maps variables to their right-hand side as they were defined at a lab binding. And we can see the top two rules, they explain how a variable could be translated. So one case is that the variable is just untouched, nothing is inlined, and the other variable occurrence could be transformed into T when there is a term T prime in the gamma environment, and T prime can be recursively transformed into T. And there's a bunch of other rules, basically mostly congruence-like rules, and this neatly captures an inlining pass. Now, it's nice to look at these rules and explain them this way, but in practice, we implement them as a Coq relation. And okay, for the simply typed lambda calculus, this is still decently readable. But for example, in the Plutus compiler, the language is much larger, and these relations are much larger as well. And on top of all the specifications per pass, we have a formalization of the type system. We have a notion of type normalization. We have type equality. We have a big step operational semantics. So we have a lot of these inductive relations. Yeah, And so one of the things that we noticed is we don't only want to use these inductive relations to build this certified compiler on top. We also see them as the actual specification for the implementation of the compiler. So we want to use these definitions as a reference for the compiler developers, which may help them in discussions about the implementation or any refactorings or just informal reasoning about how the compiler is supposed to work. But yeah, these compiler developers don't always know about Coq syntax, so this is where the original idea came from. I want to typeset all these relations as some nice inference rules in LaTeX. Okay, so how do you use this little tool that I developed? Basically, first step, you specify your inductive relation. Second step, you provide some notational rules. I'm not sure if this is readable, but okay, I'll get back to the notational rules in a second. And then you run this little Metacoq program, which then generates the LaTeX for you. So here you specify that you want it written to some file, and we run this print rules function that takes all the notation instructions and some other config. And finally, the last argument is the inductive relation that you want to print. Okay, so I think most of you here are familiar with Metacoq, but it's a meta-programming system for Coq. And I'm not using any of the fancy meta-theoretical results that have been done in Metacoq. I'm basically just interested in some reflection of the syntax. I want to inspect the inductive structure of inductives. And sure enough, if you look at the AST definitions in Metacoq, you can see there's references for referring to inductives. There is some representation for constructors inside the inductives, which is basically just a list of names paired with the type of that constructor. And then there's even already a sort of pretty printing function, which takes a term into a string. So this seems like it's just connecting the building blocks and writing this function. So here's some code in the template monad that you can do. It quotes the reference of the inductive that you provide. And then it looks up, basically the constructors of that data type, and calls this pretty print rules functions at the last line. So, okay, that seems fair enough. Let's try it out. So here's my simply type lambda calculus again. At the bottom, I run Metacoq run print rules for this inductive. What do we get? Okay, it's not great. There are some horizontal bars here. So, okay, it's at least printing rules. The point is, for example, it's including all constructor arguments. So, whereas you might want some implicit arguments, etc. And also, if you zoom in a bit, for example, here we look at this expression with cons. We have no notation like we're used to in Coq. Fully qualified identifiers, and if you look closely, this is just the first argument of cons, but it's a type argument, basically saying that it's the product of two types. So, yeah. And what's unfortunate is that in Metacoq, it wasn't possible to access this notation information and information about implicit arguments and that kind of stuff. So yeah, we have to work around that in order to get some sort of reasonable pretty printing. So to do that, I introduced a few tiny set of combinators just to handle some strings. So for example, here at the top you see a few rules for the three constructors of the lambda calculus. So this says that if you see a variable case, when it's applied to a single argument, which is the name of the variable, you just print the name of the variable. But in the case of the lambda, you get three arguments, and you can combine those three strings basically into what you would expect in LaTeX. But also in here you can mention names of inductive types. So it's not just constructor names. So this is the actual type of the type derivations. And you can mention function names, etc. And to deal with, for example, implicit arguments, you basically just ignore some of the type. So for example, here you ignore the type argument. It seems like this double arrow thing is a bit magical, because on the left-hand side it has, well, it can have constructors which are not applied yet. It can have types, it can have functions. So how does that work? It's basically using this little quotation trick from Metacoq. So between the percent signs, you can quote any term. So what we get here is basically this whole list of notations is just a lookup map for expressions to their predicting function. But yeah, we're basically using the actual notation Coq mechanism to define our custom notation mechanism, which is a bit funny. Let's see, then we have some extra configurations. So for example, we've seen that by default it would print all the premises, like all the argument types as premises. Well, we can just choose to, for example, not print any premises that don't have a dependent type, which is, at least for the example with the type system, is a decent choice. And then we can, again, implement this printing of rules in a more sensible way. And then we run it, and yay, we get the expected result, some nicely printed LaTeX. Okay, so I also looked a little bit into seeing if I could integrate this with existing documentation tools. So the obvious first candidate is CoqDoc. This is sort of the default documentation tool, but it basically just parses the source. It's very lightweight, but it doesn't really run any of the code, so it can't really compute my LaTeX representation. Then I looked into Electrion, which is a really interesting tool and much more recent. It's a collection of tools for writing technical documents that mix Coq code and prose, or also a literate programming toolkit that basically uses restructured text combined with Coq code. But most interestingly, it runs your Coq session and basically records intermediate proof states, all that stuff, including the messages that Coq produces. So it's a very interesting project, and I would highly recommend you to look at the GitHub page. It has a lot of nice examples and visualizations, but it did not yet have, well, printing inductives the way I want. So yeah, I basically just integrated that, and with a bit of MathJax JavaScript hacking, it was possible to just print this inside the web page that Electrion can generate for you. So this is just a screenshot from the browser. Right, so there's some related work. There's this OTT tool, which is a separate meta language for describing programming language semantics. And it can also print inference rules, and it even has a backend to produce Coq code. But this is a bit of the other way around. I'd rather have my definitions in Coq and just directly print them. There was an actual Coq to LaTeX tool, but it seems unmaintained. It relies on a custom parser, and it's only usable on Windows. And it also requires annotations on the source code, which looks a bit like this. And this was something I wanted to avoid explicitly. I would like to have my usual Coq definitions and then modularly or separately define the notations for printing. So some obvious next things to do would be to also pretty print simple ADTs as grammars in EBNF notation. It would be really nice if I could somehow reuse the Coq notation mechanism. And I have some ideas. I mean, this information must be available on the OCaml side, so maybe it could just be exposed in the Metacoq interface. And some other idea would be maybe to generate, instead of generating a string in Metacoq, just generate some isomorphic generic representation of an inductive data type, and then just use the normal Coq notation mechanism afterwards. I would also be interested in trying out this extractable template monad, where you can basically extract your Metacoq code into OCaml, so that it's just a bit more performance. Right now, for the larger relations I've tried, it takes a few seconds, but yeah, it's not great. So in conclusion, with this tool, you can pre-print inductive definitions that are readable for non-Coq users, and it also saves authors from duplicating their relations in tech. And yeah, it's also saving you keeping the definitions in sync. This is still very early development on this tool, so any suggestions or ideas are welcome. And thanks for your attention.
Yeah, thanks a lot for the talk. Do we have questions in the audience?
Hi, I was kind of curious. I mean, no, the Coq notation mechanism is quite strong. You can do a lot of hackery there. And you can get, I think, a pretty good-looking ASCII art-ish version of your inductive definitions if you use this kind of, use and maybe abuse this notation system. Did you try something like that before going for the much more ambitious version that prints out rules? Or like, because I mean, the point is that you want something that's readable by people that can't read Coq code. With enough notation, you can have something that's readable and that's maybe less difficult in terms of work than full-blown LaTeX support.
Right, so maybe it's possible, but I couldn't find a way to basically inspect the structure of an inductive definition. Like I know notations can be used for expressions or terms, but yeah, this is like a sort of meta construct that you cannot really inspect.
Okay, yeah. Oh yeah, so you still need to keep like the pipe and stuff, and that thing you can't do anything about. Okay. Yeah,
right.
Yeah.
Yeah. Well, so unless this this second option of generating some generic representation through Metacoq, okay, you have an object, a term you can inspect and use some interesting notation for.
Yeah. Okay. Yeah. Thank you.
All right, let's thank our speaker again.
Are you using that mic? I think it's also working, so let me just switch it off.
Yeah, we'll do. Jesus Christ.
All right, our next speaker will be Romain, telling us about new foundations for Coq IDEs.
Thank you very much. Hi, guys. So, yeah, for those who weren't here this morning, I'm Romain Tetli, and I'm the new hiree in the STAM team with Yves. So I'm a permanent research engineer who's working on IDEs for Coq, and particularly on VS-Coq2. And today I'll be discussing the foundations that we've been building to further maintain and develop VS-Coq2. So this isn't a bold statement on my part. Actually, this is the title of a paper from 1992. And the reason I thought it was interesting to put this out there is after discussing with the community and things like that, it seems that things haven't changed that much in the realm of IDs for Coq, at least in the sentiment that the community has been giving me, which is that it seems to be lacking strong IDE support. And that's a real shame, because if we're going to use this for industrial applications and like that, we really need good IDs. So of course then I'm going to talk about how to develop a real ID, I suppose. And that starts with what really has changed since 1992. And I suppose one of the bigger things is, well, the LSP protocol. And when you develop IDs, a common idea is, of course, you need new language features such as completion, diagnostics, things like that. And it becomes very natural to imagine a separate protocol, a separate executable from your editor to handle these things, which we usually call a language server. And actually, it's also very natural to the Coq world, as in old papers, they discuss this concept very well. a server then that is separate from the IDE to develop these things. And in recent years, there's been efforts to standardize this through a protocol called the Language Server Protocol, so LSP for short. And very basically, it's quite simple, really. If you have a common editor and a user opens a document in that editor, the protocol will then send a notification to your language server, which is in this case called text document / open with parameters. In this case, the document that needs to be passed by the server. Maybe the user will edit the document and then a different notification will be sent to the server with the changes that need to be applied. The server will do its thing. Maybe there'll be errors, warnings, whatnot. And the server will then send back a notification with these diagnostics and how to display them in the front end, so the editor. Now, of course, this applies very well to a common programming language, but the typical feedback loop for Coq is quite different, so you need to adapt LSP. And you could have the same scenario, but then you need to execute a proof, and of course you need feedback for that. So you would have the same thing. You open a document, you send it to the server, and then maybe you want to execute your proof by typically doing an interpret to point, something like that. So you will then need to create a new LSP verb. So in our case, we call it, for example, VSCoq / interpret to point, so to extend LSP, and we give it a position, the document, and the server will do its thing and send back all the information required to display a proof. So in this case, just a proof view, maybe some information on where to move the cursor and go on. Now, if you're following, you'll see that developing an IDE requires maintaining a structured view of a document model, at least. And in most instances, this is quite trivial, and then this is fine. The work is almost done. It's just a matter of plugging in. It's just a piping work, and that's great. But in the case of Coq, of course, maintaining such a model usually requires to execute it, in which there's quite a big problem because execution tends to be quite costly. So the solution we found to that is separating parsing from execution. So it could be that actually you couldn't do that because for some reason parsing your document requires to execute it, but this is not the case for Coq. And it's not a trivial task because, of course, the parser for Coq is extendable at runtime. So off the top of my head, like stuff like notations, are commands that can change the parser. And so this is supported since Coq 8.18, and we heavily rely on that for the development of VSCoq 2 to maintain that structured view of the document. And of course, if you go back to the idea of adapting LSP for Coq, then it becomes quite obvious that when you open the document, you edit the document, things like that, that only requires parsing, and that would be the parsing stage of Coq. But then as soon as you start executing stuff, then you go into execution mode. So I'm going to discuss a bit more VSCoq 2 in practice. And I mean, first, the obvious question is why VSCoq 2? There's a perfectly working VSCoq 1 at the moment. And I'd say the 3 main points is, well, first of all, VSCoq 1 does not have a real language server because it uses a hack to communicate with CoqTop and get the information. The codebase is becoming quite difficult to maintain and so needed some renewing. And that is mainly due to the fact that there's a bit of data technology in the front end, which makes it difficult to do dynamic UIs and things like that. So the VSCoq 2 is organized in 2 modules, one of which is the language server, which is written in OCaml and uses a reactive programming pattern, which I'll come back to in a minute. And the client is written in TypeScript, to work with VS Code, of course, but using the React framework, which makes it easy to make dynamic, reusable, interactive UIs. In fact, it uses 2 independent web apps that have been completely independent from the extension and could be reused in different environments, even maybe the web, the goal view, and the query panel. The architecture of the language server uses low-level modules, such as the execution manager, a document model, to communicate with Coq. So of importance here, you have the execution manager that's going to communicate with the Coq vernacular and handle everything execution-wise. We have a little query module that handles queries such as search, locate, check, things like that. And we have our document model, which communicates with the Coq parser. All these things use a reactive programming pattern. They will create events which will bubble up and then get handled by the top level. So, and go through LSP manager, which will handle everything LSP-wise. So receiving notifications, sending out notifications, receiving requests, handling them. Rather than blabbing on about it, I'd rather show you how this works. Very quickly, I'd like to give you a demo. Oh yeah, nice. Jesus, that's gonna be interesting. So I'm gonna do something a bit crazy. I'm gonna run a development version of VS Code. There we go. This is gonna be a little difficult. Wow.
Yeah, try zooming in. It's hard to read also for us. So.
Sorry?
In Control Plus or something like that.
Yeah, no, that's great. But I would really like to see. Yeah, I think that would be better. You're right. Okay, hold on a second. Yeah. Okay. Ah, there we go. That's way better. Okay. Let's just run this again. Yes. All right. Wow. That's a bit intense. Yeah, I'm falling prey to the typical demo effect. Sorry. This is way too big. And is this better? A bit smaller. Great. So I'm running an instance of VS-Coq on a file that I'm using to teach engineers at the Inlia engineering team how to work with Coq. So at the moment, it's using a new sort of interaction model that maybe you wouldn't be used to, which is a continuous mode. It's running the document continuously, and if I move the cursor, it will trigger a goal view, which of course, right now you're not seeing greatly. So, if I open the user settings here, you can see that I'd like to demonstrate that these views are quite dynamic. In this instance, I'm displaying the several goals I have here, which are collapsible, but I could display them as tabs if I just change this little here, and you see it goes very fast, although, well, I'm sorry about the display, but this mirroring thing is just not working great. There's a few other stuff that we've implemented. So some students have implemented some basic version of auto-completion. So in theory, if I go here and I try to type unfold, abstract, transfer, it should come up as an autocomplete option. Other things I'd like to show you are maybe so we have a query panel implemented in which we can, well, search things, but also use other queries, like maybe locate, check, about, you name it. We can, of course, add tabs and remove them. And so I'm going to show you a new feature that actually we've implemented last Wednesday within Code in RIA. You can see here I've got a warning triggered by the intros. And if I hover over it, you'll see that it tells me intros is fragile and I need to specify the names. So this is, of course, because, well, we have an apply H later, and if we start refactoring this code, it could cause havoc. So if I hover over it, you'll see I also have a quick fix handled here. And when I click, it offers me already the option that I can then just, well, change, and there we go. It fixes your code. Wow, thank you. In fact, this is The great thing about this is because of the way we use the LSP protocol, it doesn't require you to re-implement it each time. So now if you just change the Coq API and add new warnings with the correct information, it will work. So I can prove this to you. By the way, the interaction mode is of course changeable. I could go back to a more traditional manual mode, like in here. And then I could do interpret to point here. So in this case, well, here Enrico, I think 2 days ago, implemented a new warning, which is we create a module, we try to do extraction on it. Of course, it's ambiguous. And once again, so he only corrected the Coq API to add the correct information. And if I click on it, then I'm going to get, well, both infos, and I can just click, and there we go. So I hope I've convinced you that this refactoring was actually worth it and makes it really easy to implement new features. I think that's about it for the demo. Now I'm going to try and find my, there we go. And to give you a rough idea of where we are at the moment, so we released VS-Coq 2 in September. There's been 3 minor versions since then, and we're working on some stabilization at the moment, and we hope to roll out quite a lot of new features after March and in the coming new year. So you'll see quick fix, probably also stuff like jump to definition and things should come quite quickly. I think I'd just like to conclude and give you an idea of what we'll be working on. And if I had to give you some take-home messages, I hope that I've convinced you that VS-Coq 2 is at least better maintainability than the VS-Coq 1. That LSP support allows for easier language feature development, as I hope I've demonstrated, although poorly because of this little mix-up. And well, it's of course an open source project, so contributions are welcome and encouraged, so please come help us. And in terms of further work, as I said, for VS-Coq 2 itself, we'll be focusing on debugging and stabilization in the coming months and then new features soon. But I'd also like to talk about Coq and LSP. So for Coq, I think there needs to be improvements in the API, and this is something we should do together, at least to know what the warnings should give us. Maybe we could specify this. This was a proof of concept in this case, but this should be clearly specified. Having locations of functions would help us well do everything like jump to definition, better autocomplete, and things like that. And to display the goals in the front end right now, we're using a really hacky solution because we use quite a dated system, and it would be really great to also specify the information we want to display in the front end as goals and how we send them through the protocol. For LSP, I think this call has already been made before. I think probably by Emilio, he'll correct me if I'm wrong, but it would be great to standardize the extension to LSP for interactive theorem provers. I think the extension that we've used could be standardized to include other theorem provers in the long run. And I'd say that's it. Thank you for listening, guys. And if you have any questions, I'd be really happy to answer them. Thanks.
Thanks a lot, Romain, for the talk and for daring the demo gods. They were partially with us, I guess.
Didn't go too well, man.
Well, I mean, we got a demo, so could have done a lot worse. I've seen much worse.
Hi, thank you very much for the talk and for the tool. Very nice refactoring with this intros. Could you please do the same for like proof using?
That's really, really funny you should mention that, because that was the thing we were working on, like I believe yesterday with Enrico. Like that's the third thing. We were thinking of stuff to show. One of it was intros, one of it was the module thing, and the other one was proof using. So yeah, definitely. It's the idea is to do it, yes.
Thanks. How soon to expect?
Probably next week. I don't know, man. Like it really depends on when we roll out the next release and if we plan to introduce the quick fix, because it's not just a matter of changing the SCoq in this instance. It's also changing the Coq API itself.
Okay, thanks.
Yeah.
Again, thanks for the talk. I just want to ask, so since multiple editors support LSP, not just VS Code, could we use this in Emacs and possibly to replace Proof General?
Yes, in fact, I believe there's already been an effort to make it work with them. I can't tell you the exact name of the repo, but it has been done, yes.
So
this is IDE part. Have you thought about any tie-up for the documentation? So you can.
Yeah, that's a loaded subject, man. But yeah, I did. It's an ongoing thing. It would be great, yeah, to have included documentation with it, and probably some tutorials as well directly included in the panels, probably as a web app or something. So yeah, there's some thought to it. I wouldn't say work yet, but hopefully soon, yeah.
To add to that, like in other languages, I can hover over a function name and it shows me like this doc comment thing, which is like modern technology from the 90s or something. Could we have that for like comments we attach to Coq definitions via whatever syntax we need for that?
Yeah. It's also something we'll be working on, and part of it is also changing what information we want to transmit through the Coq, through the protocol. But yeah, of course, yeah.
Sorry. So this is great. I'm very excited to see that. I think we'd love to move Proof General away from what it's currently built on. So that would be great. It's more a suggestion than a question. There's actually a lot of features in Proof General and the extensions that exist to it. So the automatic intros, Proof General does. The automatic proof using, Proof General does as well. And so I think at some point and it's fairly decently documented, taking that list and having that as a checklist would be very helpful, I think, to help some of us move away from that.
Thanks, man. I'll take that to heart. Wow. Maybe just scream the question. I don't know, man. Like.
So the degree of speed in this demo was very impressive. Have you had any examples where you have Coq proofs that are really slow, and what does that do to the user interaction? Like on the order of hours or days for normalization?
Days.
Some
Jesus
of us
Christ,
have
man,
that
come
as
on.
part of our experience.
So yes, there's definitely issues with some files. Not gonna lie, it has been a problem. And what I would usually say in those instances is go back to manual mode. Like, this is why I think keeping both is a good idea to some degree, and probably making it more, at the moment it requires to go in a menu to change it. At some point I was thinking of making that change with a shortcut or seamless, so that to make it easy for those instances. Yes, definitely.
Okay, thank you.
Let's do one final quick question, and the next speakers can already start setting up.
Thank you for this work. It's very nice. I'm a Proof General user, and I would really like to switch to VS Coq. There are several things that have stopped me from doing that. One of them is the stability, which you're working on. Another one is that I really like that in Emacs I have a lot of shortcuts, like for queries that you showed. I don't want to open a separate window to make a query. Can you do that?
Sure, I was actually discussing that very same thing with someone else here earlier today, but yeah, we can do that, and we're working on it. So a lot of these shortcuts are already, in theory, implemented. We just need to plug them in. Oh yeah. Thanks.
Okay, one final quick question.
So I'm going to mention Lean. Lean has an LSP server and an Emacs mode that uses that LSP server. Can we reuse that and their LSP API as well, or not?
Sorry, can you repeat?
Lean 4 has a built-in LSP server, and it's also a proof assistant, and they have an Emacs mode. And so in the spirit of unifying, how far is our API from their API? And could we reuse their Emacs mode directly? And their VS Code mode and so on.
You want to use the Lean 4 server with Coq?
No, I want to use the same protocol as Lean uses.
Yeah.
So that because when I use Python or JavaScript or something, I don't install a specific mode typically. I just load the LSP server.
So you're asking if you can reuse that language server with a different editor?
Their editor UI with a different server. Could our Coq server speak the Lean LSP protocol?
Well, that goes along what I discussed in the final slides, which is we would need to standardize the extension to the protocol, and in theory it could be possible, but at the moment I don't think so. No.
All right.
All right. Let's thank our speaker again. And it looks like the next talk will have 2 speakers. Second talk about editors today by Emilio and Bhakti.
Hi folks, it's my pleasure to do this talk jointly with Bhakti. We've been having fun and working on this, and actually here, we are here in particular, we're going to present work we've been doing is on a different language server for Coq, which has quite a different design, which is called Coq-LSP. And in particular, in this talk is about how do we solve one of the most common problems users have, and maybe as people have been asking questions, how many people have found this bad version number when using Coq? How many of you have seen the message? I kind of believe then you don't never use Coq if you if you never found that. But indeed, that's actually something very interesting in different contexts. And as of today, the experience to working, one of the things we do is we work with very large theories that are a composition of many other theories. And indeed, one of the main troubles we have is a big pain because there is a lot of manual steps. You need to edit a file, you need to go to type or to click a button in the editor integration is not so good. The Coq only knows about a file, then you need to go to make or you need to go to Dune. This is going to integrate poorly, right? And actually, the idea is like the problem actually, and something we were just discussing today, right, is that actually the reason the user experience is really bad and the developer experience is even worse. So this is, of course, if the developer have to in order to improve this, they're going to find a hell. Then actually, I believe this is a reason. There is a lot of codependency. You know, for example, in Metacoq, they developed the tactics at the proofs at the same time. I think in Coq, we tend to separate things, but actually, I'm not sure this is very sometimes productive. And indeed, something I've noticed, I work a lot on build systems unexpectedly, but something I've noticed is the programming model to integrate a build system with something like Coq-C is really bad, it's really complex, you have a lot of races, a lot of process handling, portability issues, you know. General purpose build systems, they adapt very bad to the domain of interactive improvers, and I think Lynn and Isabel people, at least is the people I know more what they are doing, they totally agree with me. Many other people don't, but I think actually many people come to me and say, but you're going to fuse a build server and an interpreter or a LSP server, and actually they come and they say like, the Unix approach works, but actually this is totally, I've thought a lot about that, this is totally false, this is a myth. In fact, try to maintain a bash script. You're going to see, of course, maybe bash, you're right, or a Python thing which is untyped, and try to maintain that. I give you a bash script and try to maintain to do a change and verify it or test it. It's really complex, this Unix model, it doesn't work so well. In particular, a lot of extremely important things here. Okay, which is, for example, you need to communicate a lot of things, for example, for what Roman is doing, he needs to communicate the warnings, etc. You die if you need to do a protocol with the build system to maintain the protocol. So you have portability, like, okay, try on Windows, like try to deduplicate the stuff, try to think when two objects are equal. So really this is a really bad experience. And indeed, what we are going to discuss is 2 key ideas, which are also the foundation for the whole server, but actually we're pretty happy with them. And one is an idea that Andrei Mokhov promoted, one of the Dune developers. They were at Jane Street. They have experience with very large industrial code bases. So we had this Dune meeting. I was invited just before the pandemic, and actually he told me, and Jeremy, of course, and Rudy, many other people, they gave a lot of insight on this. But they actually told me like there was this big field that fusioning build systems and compilers, incremental computing. And I think they're right. This is still an open research topic, but myself, I'm pretty happy. He knows way more than I do, but I think that was a good approach. And then the reason is how to do that thing with some methodology that comes from before. We have a methodology based on interpreters from before to do CertAPI and to do things in an easy way, in a very maintainable way. Actually, then we developed something called Fletch, which is actually based on reactive incremental interpreters. Here I need to cite Leo de Moura. He gave in a link together. He said like incrementality is the most important thing for user interfaces. I think he was just echoing what Microsoft VS Code team thinks. But actually that stuck in my head, and I say, oh, I never think about incrementality. It's very different incrementality from parallelisms, you know, sometimes. Anyway, so on top of that, you have Coq-LSP, you have also a new Coq compiler that can do a lot of things. And yeah, well, there is a lot of stuff. And then, but the key idea of Fletch, the key idea is the extensive use of algebraic effects. And I'm gonna let Bhakti now to proceed to present what we have done to solve this problem of how to never fail in our require.
Yeah, so that magic number error was something I got a lot and never figured out for some reason. And was talking to Emilio about incremental computation, about algebraic effects somehow, and we were like, OCaml5 has a new algebraic effect system. If you're not aware, algebraic effects are just a way to model suspending and resuming a computation. Pretty simple. But we decided to kind of explore this application domain in Coq-LSP. And so what we did was we decided that, like, really, if you hit a require statement, it should just perform a side effect to, like, check the program, to check the file that you're depending on. And so what we ended up doing was pretty simple, but it took a long time to come up with somehow. But if a require statement is encountered during interpretation, we perform this require effect to read the contents of the file. Literally exactly what's on your screen. And this was pretty simple, but basically what makes it interesting is the handler here, and we wanted things to still be incremental, right? So we would ask questions like, is the required document ready? And if it's ready, then you can resume your continuation with the contents of the document immediately. You don't need to do any more work. If the document isn't ready, you want to mark it as pending so you don't accidentally say, hey, this document is ready when it's not. And then you want to add the current document to the reverse dependencies of the required document. And reverse dependencies is just a way of saying what depends on me, not what do I depend on. And finally, you would add the required document to the scheduler queue, and that's just running. So in the background, at some point, hopefully it gets checked. Okay, that's cool. What does this mean? So we have an idea of a document state, and it's kind of simple. There's only 3 states your document can be in. It's either in the initial state, it's completed, or it's pending, and it's pending on some other file that we're waiting for. And these are literally the only 3 states your document can be in. And we store the state in like a hash table, and we have a bunch of handles that store information about your document. And so with respect to checking, if the state of if I say check this document and it's completed, I really don't need to do it again, which you would be surprised. There's editors that would do that. If it's in the initial state, then all I have to do is check it. And if it's marked pending, then I check whether the document it depends on is completed. And if it is, then I resume the continuation with the contents of the dependency. Sounds really simple. Here's an example. Looks like a lot of text, but all I'm doing is I'm making in document A, I'm making B, which depends on A, and I'm making C, which depends on B. And then I'm making D, which depends on B and C. I say I want to check B. What happens first is it tries to check B, and now it says, well, B depends on A, so I have to check A. And now it tries to check A, but you know that B is in the reverse dependencies of A. You need to keep that in mind. A checks, we're all good. And now we're back to B, which is in the pending state. And finally, once we find out that A is completed, then B can also complete. Now we say check D. D is gonna first try to find B, and it finds it, it's completed. It doesn't need to recheck it again. So then it's gonna try to find C, and obviously C is gonna say, well, I have a reverse dependency D, and same thing's gonna happen, and then finally you're gonna have B, which is not checked again, which is like the main thing here, that we are really not trying to do the same thing twice. And finally you end and everything is good. And you might be thinking, what happens when you update a document? Well, we discover our reverse dependencies dynamically. So it's not like at any point I have a full dependency graph of how everything looks. It's really when I kind of look at something, I know what its dependencies are. If I haven't looked at a file at all, then I don't know anything about it. I haven't checked it. And that's fine. I only want to do things not eagerly. I want to do things like just when someone asks for them. It turns out we get like, it's like we get errors when we have cyclic dependencies for free. This just happens because there is no valid state where we have no valid states for when there would be a cyclic dependency. And this was something we thought we would have to handle manually, but it just happened. When you update a document, you would invalidate it or mark it as pending, as well as all its reverse dependencies. And then there's like a little beacon in your environment to indicate that your environment has changed, so you know that there has been a change that has been made. And like I said, you only check a document when it is demanded, and not like I have kind of a big library and I check all of it at once, as you would if you did make. So yeah, why would I do that? Maybe Emilio will tell you.
Thank you, Bhakti. And a little bit on the evaluation. There is a qualitative evaluation, and well, you will say, what is the point of this? And the point of this is actually we are advertising this build system because, well, this prototype Bhakti show is very, very simple. Though, as you mentioned, it's tricky to understand the flow sometimes. But actually, it's a very interesting build system. So it has a lot of options, including a very interesting soundness proof we are thinking about. This is really future work. And it's really efficient, it's a great experience, and it's very portable. So for example, this is going to solve a lot of problems other tools are having. Like for example, CertiCoq. Try to run in the browser a full Dune thing. I tell you it's not, well, some people like Shahar can do it, but not me. And actually the difficulty is the beacon, this beacon or this kind of tokens of memoization. This is also very tricky in Dune. This is something for now it's very simple. We need to gather more data. And actually, by the way, like to deploy this in OCaml4, actually, it's a bit tricky. It's a bit tricky to get this in OCaml4. And Coq has, for example, now we are stuck to release this, and some problems with the Coq API is very common, right? But in principle, I think we are happy. It was fun, and it's gonna help some projects like CoQ a lot. And quantitative, and actually this we put an emphasis on the draft. So I want to advertise this. Benchmarking is very difficult, but actually I got interested in this because already one of the things we build in Coq-LSP is very interesting performance tools. Like if I started in CoQ, always understanding performance is very tricky. And indeed, so when we build Fletch and Coq-LSP, there is a lot of performance info. And I was always seeing require, a problem with require. I found many problems like this in Coq, right? Like nobody's aware, like there are ghost problems. And actually, I don't know what happened, but it was like a question like, for example, the standard library has 585 files. But do you think, okay, sorry, this was supposed to be hidden, but how many times do we parse VO files? Guess. So actually, we parse VO files 65,000 times. So even if people tell me, hey, Emilio, this is it's not so expensive, I can tell you, actually takes like 8% of the build time. That, of course, with this interpreter, we can memorize the require. So actually, it's 8% faster just by, if we didn't have to fight with some stupid API of Coq, it will happen like a very small change, right? For example, for hot, 5.5% of the build time is, we already parse 30,000 files. And I like this example because this is an example like actually if you have to do this with Make or Dune, you're going to really struggle. Okay. You're going to really struggle because just copying is going to kill you, so you're not going to get this performance benefit. So this is a clear example. Another example I like to, and I will pass the mic to Bhakti to conclude, but this memory use, for example, like Coq-LSP was built from the scratch to have multiple files open in the same process space. And for example, like you can do an experiment with this patch enable and without. And we are happy to my computer if you're curious. I don't know if we have time today to show, but I'm happy to show in a slip. So for example, you import reals twice. So for example, Coq-LSP is able to share. So already you have half the memory consumption. Though it is true like in normal Coq, you can do a bit of GC and you get back, you recover like 200 megabytes. But already look for example, this really matters. This is another example, the integration is giving us advantage and quite a few more. But I think we are ready for now. I will mention very briefly, in future work, actually, this has been discussed in CoqPL more often, but actually thanks to there is a very interesting interaction of the incremental engine with the build system. So for example, imagine you require a file, and then you say, oh, I need to wait for the file to build. So actually, Coq-LSP can actually build this file very quickly, like just an interface, load the file in memory, and then in the background, fill these holes in such a way, like error recovery, this is related to error recovery, so in such a way, like it's a very simple, you just need to be sure that memorization, that the proof is not filling a hole really, it's a bit different conceptually. So then, for example, you can get all the proofs and you don't need to require your document again. And unless, for example, the proof really changes something global, then it automatically happens. So you need to, the nice thing of this is no special support is needed. Only a patch to Coq to separate the state of opaque proofs from not. And the second point?
Yeah, I mean, I'm really interested in this question of how incrementality in an interactive proof assistant differs from incrementality in a programming language. And I think for something that is so interactive, we should be focusing on something like this more. So if you want to talk about it, I'm here. But that's our presentation. Thank you.
Stay tuned for the next release that will include this. Yeah.
All right, do we have questions? Yes.
Thank you very much for the talk. So when is the release? When is the release?
Actually, it depends on the time we have. I don't know. I think Bhakti after all this week maybe needs to rest too a little bit, right? So, but yeah, hopefully the prototype we're quite happy. So maybe at least I can give you a pull request if you want to try. But I think it's almost ready to release in OCaml 4. Yeah.
Mm-hmm. Thanks.
Thank you. I'm always afraid of standard proliferation, so I wanted to ask, what are the input of your system? Do you read a Dune file, a Coq project, or is it another file format to know the shape of what you actually need to build?
Well, I can answer that. For now, we only support Coq project, but it's just unfortunately lack of resources. This is not important in this setting. Like we have a model which corresponds to the internal Coq model of the libraries, and then we are able to read Coq projects, and hopefully, if we get some time, to do projects. This I cannot promise I will have time to do myself, but it's very easy if somebody wants to do that. So in principle, yeah, we can. This is independent of the metadata. You can, in fact, something very important here is inference. By the way, so actually, for example, it's very easy to, because of dynamics of the internals, is you can infer whatever you want. So this is modular, so not a problem. Though you need to map whatever configuration you have, you need to map it to the Coq representation. This is the ground. This is the truth, what Coq thinks about where the files are, all this, yeah.
So I was wondering one thing. From the sketches you showed, it looked like when you hit a require in a file, you will then wait for that dependency to be handled, and then you go on and handle the next require. So if I have like 5 requires in a row, would it do one after the other? Because if I do this in proof general, it will actually build all the 5 of them in parallel.
Well, that's a great question. So actually for now, and this is a strong limitation, at least at this point, is actually we are single-threaded. But in principle, once we support to, and I like that because for JSCoq it's important, But in principle, there will be no problem in doing it in parallel if we adopt like a single, now we have a scheduler queue is linear. So this scheduler queue can become a bit more complex and you could do in parallel. Like, I don't see a problem with that other than, of course, it's a bit more tricky to program. But actually that should be possible in OCaml 5, for example, using, do all the files in parallel. Because actually what the handler does, is if backT goes back to the slide, the handler, it just pushes into a queue. So then in the queue you can in fact like use standard scheduling strategies to maximize. So in this sense, you stop the document.
But you will have to go on in the original document after the require. Like usually you couldn't go on because there's something missing. But some of the following commands you can do if it's just another require.
Yeah, that's a great question. But actually, this is a bit more complex. But actually, you can indeed, if you would like to be eager, you can do a speculative execution of the document. But that's a great point, actually. Yeah, maybe that will be necessary. Yeah, so actually that's a great point. But there is no problem. There is no problem in doing that actually, because imagine you interpret it's like errors. Imagine you interpret the requires unsoundly. Then when the things become sound, it will recheck itself. So that's okay to do.
Okay, thanks again. All right, our next and final talk is going to be by Ambroise about category theory diagrams.
Okay, thanks for the introduction. I will start with a naming convention. I will refer to my editor as YAD for yet another diagram editor. It's not totally satisfactory because there is another software called yet another diagram engine. So sometimes I prefix it with CoReact, which is the name of NR project, which is about Coq-based writing towards executable applied category theory, in which I am involved. And there is, if you can check it, there is the website link on the slide. If you get bored during my talk, you can go on my website and try it online. Okay, how does it work? Maybe I should, because there will be a demo at the end, so I should first figure out how to show my screen. Display setting. Yes. Okay, it's not ideal, but we'll do like that. Okay. Okay, so this is my website, and you go here, and you get the you get the editor. This is the tutorial, and once you have read it, there is a small exercise that you can try. It's basically replicating this square, but without using the mouse in 4 actions. Okay, but this is not. Okay, let's come back here. Okay, so it also comes with there is also a standalone desktop version which embeds the web app using Electron, and it also comes with this. This standalone version comes with mechanization feature that I'm going to describe in the following. But before that, I want to mention Quiver, which is another software for editing diagrams. It's also runs in your browser, so it's quite nice. I want to do a quick comparison with this editor. So it's about the same size in terms of lines of code. Quiver is mainly implemented in JavaScript, whereas my YAD is implemented in Elm, which is a functional programming language. Quiver is more user-friendly and have a lot of styling options. YAD has more editing features, so you have tabs, copy and paste, find and replace, or expand selection to connected components, kind of things. And in both cases, we have a LaTeX export. But the main thing about YAD is that it comes with mechanization features. So I'm going to introduce them now. So to begin with, just to explain a bit the architecture, how it works, that you would run the editor in the background, the standalone version, and then you will also run Visual Studio Code with my custom VS Code extension, which builds upon the Coq-LSP extension. And then there is also a Coq library for custom notations and for category theory. So what can it do? First, it can show, if you move your cursor somewhere in the file, it will show the diagram, it will show a diagrammatic representation of the goal or of the diagram if it's relevant. The other thing that it can do is that it can generate a proof. So you draw your diagrams and with you embed the proofs in the diagram, and then it will generate a proof script that show commutation of the outer diagrams. I'm going to explain a little bit more about that. With a simple example, even if you are not too familiar with category theory, there is a easy result that if you have one natural transformation, alpha from F to G, and another one, beta from G to H, then you can define the composite natural transformation. And so it means that this diagram commutes for all function morphism F. So saying that it commutes means that both branches here are equal. So if I compose H of F with beta C1 and alpha C1, which is this composition here, the left-hand side, then I should get the same thing as beta C2 composed with alpha C2 composed with F of F, which is the right-hand side. So the diagrammatic proof would consist in splitting this diagram in two sub-diagrams, introducing this intermediate morphism here, G of F. And then we know that both sub-diagrams commute, so this gives a proof of the commutation of the outer diagrams. And this can be turned into a computer-friendly proof somehow, just by applying rewriting rules. So here we use the fact that the right diagram commutes first to rewrite H of F composed with beta C1 into beta C2 composed with G of F, and then we use the other commutation to do the other step. Okay? So, of course, this should be automatable, and this is what YAD can do. I'll show you later. And another thing that you can do is that you can construct diagrams step by step. So I will be a bit more specific about what I mean by that. So the thing is, you start by selecting your sub-diagram here. And then you create a proof node in the editor. And you can give it the label a Coq tactic. So here we would say naturality, for example. And what happens is that Coq, in the VS Code window, will check that this tactic actually solves the goal. So what is this goal? It's the fact that H of F composed with N of A is equal to NB composed with a whole. So this is really, so you see this this arrow here is unnamed, so it will be converted into instantiation variable EVAR in Coq. And so after that, the diagram gets completed in the editor, because Coq is smart enough to guess what is the unnamed arrow. So it will rename the arrow accordingly, and also the proof node will be saved and marked as validated. So this is a green check mark here. So just before going to the demo, I want to mention another software for mechanization of diagrammatic proof, which is Luc Chabassier's interface. So it's another architecture. First, it's a standalone program implemented in Rust, and it's relies on a Coq plugin, which is called, which introduces a diagram server. And this Coq plugin can provide the interface with goals and assumptions and the available lemmas in context. And then the interface would produce a Coq proof term that will not show in your VS Code window. It will be implicit. But you can still do print proof if you want. But, so it's not really meant to be a a diagram editor, so there is limited manual layout. And it's also nice because you have some graphical proof tactics. Okay, now I'm going to jump to the demo. So this demo is based on, so you can check it on, it's on the it's on GitHub. It's based on the category theory library of hierarchy builder, and I have also added some tactics and notations on top of that. So what is the example? So you all know that a distributive law between two monads induces the monad structure on the composite endofunctor. And we will show in particular that the induced multiplication defined by this formula is associative. Okay, so okay, it's not on the right screen. I can't see anything. Yes, but I would like mirroring. Yes, I want that, but I don't know how to. And duplicate then. But yeah, it doesn't work. So let's go back to the extension. Okay, so now I want to increase the size because I can't see anything. Yes. Okay, so all right. Okay, so this is the file. Okay, I will put this here. Okay, so this is the category theory library. Is it okay? Can you see the screen? Yeah, okay. And these are my custom notations and tactics. So we introduce a category, C, two endofunctors on it, multiplications for those endofunctors. I will omit the units because we will only focus on the associativity. I introduce some LaTeX notation for those. And this is the associativity for the multiplication of S and T. So now here is a line with a diagram. So it's called the diagram. And then the data that you see is some JSON data. If I put my pointer on my cursor on it, it will load the editor and show it. But it's on the wrong screen, fortunately. Here we are. Okay, let's try to increase the size. Yes. Okay, so this is associativity for S, for mu S. So you see, it's you have two ways to go from SX to S of X, and they must be equal. Okay. Now we have the distributive law here, and it must satisfy some compatibility conditions, which are here mu T delta and mu S delta, and here is a graphical representation, a diagrammatic representation. I will. So this is the first one, and this is the second one. I will save them for later, so I'll duplicate the tab and I rename it as compat. Okay. So what's happened is each time when you move the cursor in the editor, it's only the first tab that is going to be updated. Then okay, so this is the definition of the composite of the multiplication for the And this is what we want to prove here. Okay, so here I unfold the definition and I normalize to make it nice. And if you look at what we want to prove, here it is. So this is what we want to prove here. So I have already done the proof for you. Here it is. Nice. Okay, so let's duplicate this. I move this here. Okay, excellent. Up. Okay, so you see here, I have done the proof. I did my homework. All of these check marks are actually proofs. So if I edit them, you see, if I rename them, you can see that it's actually proof tactics here. It's embedded in a macro which is called CoqProof, which is like just a beacon for the editor to know that it's actually a proof. And you can change the appearance by updating the LaTeX preamble, which is here. But now, how do you know? So this is a proof. So it's just a diagram. So how do you know that it's correct? That actually the proofs are really validated by Coq. So there is a command in the editor to check to ask VS Code whether this proof is correct. And doesn't seem to work. Ah yes, maybe it's worked, but we can't see. Can you see that it's green now? Okay, because I can't. So yeah, so what happened is that if you look at the VS Code window here, there is this notification which says that actually it's a valid proof, and I can for example give you. Whoa, what's happening? Okay, something strange happened, but okay. Here I will change it for reflexivity just to show you that it's actually not turning everything in green. So here I get it still remains black, and in the VS Code window you get the fact that it actually failed. Okay, so now how can you do this more interactively? Let's start from. Okay, I will just show you some features now. We'll start from the. Actually, let's start back from the beginning. Yes, it's ugly, but. Okay, so let's say you want to rewrite those two. There is a lemma that allows you to. You can use compatibility of delta here to rewrite these two rows here. So I select the two rows, then I create a proof node. So it asks me for a proof. Okay, it's very small, but I'm writing I'm writing the tactic to apply the compatibility of delta with mu s. So what happened is that it has used it has called Coq, and then Coq has applied the lemma and then inferred that actually the other onside should be this. So you can go on like that. You can even do it more interactively. Like for example, if you want to, what time is it? Yeah, okay, maybe I will just show you the generation of the how you can generate the proof. So let's start from the proof that I have done at home. Save it in a new tab. And now I select the full diagram here, and I press the export command to Coq. And what is going on is that it's going to send, it will generate a proof script and send it to VS Code, to VS Code, sorry. And VS Code, now if I look in the window, you see that it has generated a proof. So it has actually asserted all the subdiagram commutations and build a proof of the commutation of the outer diagram out of it. And it seemed so, because there's a lot of steps, so it's quite long. But it seems that Coq is happy with the proof. And what does it use? It uses some associativity tactic just to, so no, the associativity is just associativity of composition in categories. And there are some also some lemmas like just congruence lemmas that are applied. And if you do not provide all the proof nodes, then it will just replace, for example, if this proof node was omitted, it will just add inserted admit tactic. Okay, I think I will stop here. Oh, okay, I have 2 minutes. I can show you something. Let's go back here. Well, okay, maybe I stop here because we are all tired. So, yeah, thank you for listening.
Thanks for the talk. Do we have questions?
How terrible can the categorical proof become? Can do things like 2 categories, or is this just normal, simple, nice 1 categories?
It's only simple, nice categories. But I mean, you are free to draw two categorical diagrams if you want. I'm doing this sometime during the weekend, but there is no mechanization support for that.
Okay, thank you.
I go. Just very simple question, Sans-Ambroise. Do you think there is interesting for you to run your editor inside VS Code, or you think it's better as a separate application?
I think it would be nicer to be in VS Code because then maybe it could be available in the web version of VS Code. But I think it will be also a lot of engineering to make this work. So I'm not sure it's worth it.
If I have my own category theory library, can I wire that up with your tool, or do I need to use your category theory formalization?
What you need to do is to define the tactics and notations so that it works. So I can show you the file that I've been actually written to wire it to the category theory library of hierarchy builder. So you need some notation like this, like just custom notations. Associated, I mean, you need to provide those lemmas. They are very simple, but just this is because these are lemmas that are generated, that are used in the generation. In principle, it could be made more parametric, but so far, yes, it works like that. But yeah.
So let's thank our speaker again. And I believe this concludes the workshop, so let's also thank our amazing organizers.
Okay, yeah. Thanks everybody for attending, sticking with us through the end of CoqPL. We'll see you next year. So I also want to do a few more thank yous, especially to the student volunteers who have been running around mics and doing the AV. And I would also like to thank our steering committee, which consists of Yves. Yves always says he doesn't do much work, but actually he's very important to the success of CoqPL. That's all. See you next year.